Okay, so Jonathan, I'm just going to do a quick overview of Snell's law and everything, right? Um,
Yeah,
Jonathan, anybody ever call it Johnny Boy? Anybody ever call it that?
don't call me that.
What is it?
Don't call me that.
But anybody ever call it that?
No,
I feel like you go be them if they call it that.
I did.
Oh my. Uh, what you don't like about him? He just sound annoying.
Yeah,
Hmm. You know, when I see when I see you, boy, I see you Saturday evening.
this. Oh yeah, right. Yeah.
I will see if it's the song and kind of grumpy. In person. In person. I'll decide.
No, I'm not gonna sound grumpy because uh, like I know I come in class right at the Pacific time, and I know that I leave in at the Pacific time. So, because this class, I have no idea when they're gonna end at all.
Oh, now that's kind of, yeah, kind of angsty.
Yeah.
I see. Okay, so Jonathan, first thing we're gonna look at. Do you know what wavelength, frequency, and velocity are?
No.
Okay, like not at all.
No. I probably forget.
Okay, it's okay. So Jonathan, we have a displacement distance graph here, and we have a wave. Now, do you know what an oscillation is?
Yeah.
So I want you to show me what one oscillation is here. Show me one oscillation.
It's like like
So it's just
yeah.
like, mhm.
Yeah.
Right? Cool. That is an oscillation. Now, since we have a displacement distance graph, we can find two things. In a displacement distance graph, you can find the amplitude and you can find the wavelength. So, Jonathan, this over here, that is your amplitude. And so the definition for amplitude. Amplitude is just simply, oh, sorry, that's not the amplitude, that's the wavelength. My bad. Do you know the symbol for wavelength?
No.
Okay, this is the symbol for wavelength. So this thing over here, that's your wavelength. And that's just the length of one oscillation, right? You notice since we have a displacement distance graph, I have distance being measured on the x-axis. So I can measure the distance from the start to the finish. You understand?
Yeah.
So that's what wavelength is. The length, one full right? And amplitude is represented by the symbol A. Now, amplitude refers to the maximum displacement. So, Shoma, what is the maximum displacement of this graph?
Go on. Displacement.
So this is a displacement distance graph. I have the displacement on the y-axis and the
Ah,
distance on the
this
x-axis.
the J max no. Yeah. Someone double VMP.
Yes, so we have, so this over here, that is your amplitude, and this over here also represents your amplitude. So the amplitude just refers to how high or low your wave goes. Yes, Ron, you understand that?
Yeah.
All right, so the next kind of graph you have. So you have displacement distance graph to deal with, and you also have distance time graphs. Well, displacement. We'll have enough space here. Okay, so Jonathan, look at this kind of graph. It's a displacement time graph. From this graph, do you think you could read off the wavelengths?
Yeah.
Hello, Cheyenne. How was president school and thing? I see you real dress up nice. It had press food and thing.
Musician.
Don't think she realized she's muted. Don't think so. Not sure what we're going on with Cheyenne. Yeah, Jonathan here, remember?
Yeah.
So you tell me we could find wavelength from this graph.
It should be. And there's this.
Oh.
No, it's
Jonathan, look at what we have on the y-axis. We have displacement on the y-axis. So we could find amplitude. We could read off amplitude from this graph, right?
yeah.
But can we read off the wavelength? That's the length it takes from the start of the oscillation to the end of the oscillation. Is my x-axis measuring length or distance?
No. Measuring time.
Right. So I would not be able to find the wavelength. However, I will be able to find the what? What do you call this?
The solution.
The periodic time.
Oh.
If you recall, any periodic time is just the time it takes for one whole oscillation.
Yeah.
That's wrong. Today we would have done that. Remember with the pendulum, I say the time it takes for it to go and come back. That's the periodic time. The time it takes for one oscillation.
Yeah.
Same thing over here, you know. Same thing over here. Yeah. So Jonathan, just realize the two differences. My advice is look at the axes so you can figure out where you could read off and where you carry off. All right. So give my definition for periodic time.
The time it takes to complete one oscillation.
Yes. So Jonathan, let's just see. It took give me a time for the period. Give me a time. Give me a time here,
5 seconds.
right? Let me see how good it is. If one oscillation is 5, what do you think this would be?
I think all
Yeah, what do you think that would be?
um 7.5.
Correct, because that is 1.5 oscillations. So
Yeah.
perfect. So Jonathan, suppose one oscillation. So one oscillation, we have one oscillation in 5 seconds. You with me so far? So in 5 seconds, you have one oscillation. Suppose I wanted to find how much oscillations it have in 1 second. What would I do on both sides? If I wanted to find how much oscillations it have in 1 second.
Divided by 5.
Yeah. I would divide by 5 on both sides. So in 1 second, we actually have 1/5 of our oscillation. So you would see that wave has a frequency of 1/5 hertz. That means every 1 second, 1/5 of an oscillation is made. Do you understand what frequency is?
Yeah.
So frequency, F, that's the amount of oscillations in how much, Jonathan?
In 1 second.
Yes. Perfect. And the formula for frequency is equal to 1 over your periodic time. And you will see that over here. If I wanted to find the frequency, I took the oscillation and divided by 5. 1/5. Let me know if you understand.
Yeah.
Right. So that's the basics. You also need to know formulas such as V is equal to what? Emma, tell them. What's the main formula you need to know?
V is equal to F lambda.
Right. Main formula you need to know, guys. You need to know that V is equal to F lambda. So that's wrong. Write that down. Main formula, V is equal to F lambda. Right, and you also need to know the formula for speed. Jonathan, the formula for speed, what is that? Speed is equal to what?
Distance over time.
Right. That's it. That's it for the recap there. So we have two kind of graphs when dealing with waves. You have a displacement distance graph. And you have a displacement time graph. Right. So time to pop quiz. Time for pop quiz. Are you ready for a pop quiz? Why the place so dead today? I don't know what's going on. Jonathan, you're so much more lively in pure maths. Is it because you like hard maths? Is it because you like hard maths more? Or like,
No, not really. Is that well I like physics and I like maths. It's just that the crash course long.
So you just get exhausted.
Crash course long. Yeah.
I understand. So, Jonathan, tell me the two types of graphs you have to deal with. The two type of graphs.
Displacement and distance and displacement and time.
Right. Let's run from a displacement distance graph. What can I obtain?
You get the wavelength,
We can get a wavelength. And
and the
what?
frequency.
Nah. Mm-mm. In a displacement distance graph, you don't have nothing. You don't have anything with time. Nothing with time. You understand?
Okay.
So you can figure out the wavelength. And what is the wavelength?
Wavelength. Wavelength is one full oscillation.
That's the length of one full oscillation.
Huh?
Length of one full oscillation. The length.
Yeah.
And what else you can get from a displacement distance graph?
Um, I'm not sure.
Displacement.
Okay.
Nah, that's not the answer. How does it say
Oh.
displacement? It's how it A. The what?
The A, I'm not sure.
Amplitude.
Amplitude.
Yes. And the amplitude is just simply the maximum displacement. Right? Cheyenne, what's the other kind of graph is I will work with? Then here in Cheyenne, Jonathan, what's the next kind of graph?
Displacement versus time. Displacement time graph.
And what can you get from a displacement time graph?
The period, the time period, the frequency,
Right? So
and the
period,
amplitude.
I can get the period, I can get the frequency, and I can get the amplitude. Perfect. And Jonathan, what is the formula involving frequency and time? I'm sorry, frequency and period.
Frequency and period. That's frequency and period.
Yes, have a formula, I don't know for that. It have frequency and period. If I wanted to find the frequency,
Frequency is equal to the amplitude divided by the period or something. Or like
No.
the period divided.
1 over the periodic time.
Oh,
Let me show you the explanation for that again. If one oscillation take 5 seconds, and I want to find how much it have in 1 second, I will divide by 5.
oh yeah.
So it's just 1 over the periodic time. That's all. So that's frequency. Frequency is 1 over period. And vice versa. Your periodic time is also the same thing as 1 over f. Right? And what formula have the f and lambda in it? What's the other formula you're supposed to know, Desron? So would be
B equal to F lambda or lambda, what do you call it?
lambda, yes. And lambda is the what? Lambda is the what anyway?
Are the wavelength?
Correct. F is your what?
It was the frequency.
And V is your?
And V is the
veloc.
how is the velocity?
Right. We quick thing here. Frequency is measured in what? What is frequency measuring?
In amplitude?
Oh, frequency is measured in hertz.
Oh, it's
AC. And the SI unit for that is S minus 1. Right? Because look at it, 1 over time, which is second. So that will be S minus 1. Right? What is the periodic time measured in?
how much in seconds?
Right? What is velocity measured in?
Velocity is measured in um not sure, huh?
Meters per second. MS minus 1. Right? And wavelength, what is wavelength measured in? Here's a wavelength.
Wavelength is lambda.
Here's a wavelength. Lambda is wavelength. But here I say it, wavelength.
Or meters?
Yes, it is meters. Right, so just be aware of that. Anybody want to copy down anything?
I don't copy down long time.
All right, Jonathan, you have to copy down anything?
No.
Let's move on to some questions now. So, Jonathan, give us a read.
Write in the wave equation velocity, V frequency, F and wavelength are related. Write the equation. I don't know who Bird was at.
What is it?
I do not know who Bird was at. Anyways, write the equation velocity, frequency, and wavelength. That is dv equals F lambda. Thing.
Yes. Everybody should be fine with this question, right? And Jonathan, read part 4.
A wave motion has a frequency of 10 Hz and a wavelength of 250 m. Calculate the speed of the wave.
So, tell me how I want to do that question.
You'll have to use the same formula that was up above. So it'll be 10 by 250.
What going on with it? That's your Nazi? That's on your one? Yeah, and Jonathan, what are we?
2500.
And where's the unit for velocity?
ms minus 1.
Say no more. Jonathan, you getting 3 marks in the exam, right?
Yeah.
Nice.
I just what happened, right? I just forget the thing, so I just be completely like it is when I read a question, right? And it's like I don't recognize what to do. Like I know what to do, but I don't recognize it.
I see.
Basically.
Get into the habits of underlining things. That will help you out. Underline the information and analyze.
Right.
Right? So, Emma, I'm not calling on you because I feel like you're okay with these things. Are you okay with these things?
Yeah, I'm good.
I'll call on you when we're dealing with refraction and things. All right?
Yeah.
All right. So, Jonathan, get this question, Harry.
Figure 4 shows a sinusoidal wave.
Sinusoidal.
Sinusoidal. Indicate the figure 4 to the amplitude of the wave. So I
Right.
look for the amplitude.
Mm-hmm. The amplitude.
This displacement time graph. So it's just 0.5. 0.5 and minus 0.5.
Were you just gonna put 0.5?
No,
Yeah or no?
no, I was not going to just put 0.5 because it's go both up and down.
No, 0.5 is correct. The amplitude is 0.5, right? But look what they say. They said in meters.
Oh,
Yeah. So, Jonathan, here we are. If you're going
you
from
have to multiply. No, you have to divide it.
so if you're going from millimeter to meter, we have to do. Sorry, millimeter to centimeter.
Divided by 100.
We have 100. Now, how much centimeters we,
No, oh, no, no, divide by 10.
right? So I just write
And
that,
then from centimeters to meters is 100.
right? So 10 millimeters does make up 1
Wait,
centimeter.
can we just divide it by like 1,000?
Yeah, but I'm breaking it down for everybody now,
Oh, okay.
right? So 10 millimeters is equal to 1 centimeter. And after that, after that, 100 centimeters will make up 1 meter. So going from millimeter to centimeter, that's a divide by 10. And then if I want to go from centimeter to meter, I will divide by 100. So altogether, we divide them by 1,000. Right? So millimeter to meter, that's just to divide by 1,000. That's wrong. Remember doing this morning, things like this.
Yeah.
Right. So that's wrong. If you want to go from millimeter to meter, first of all, you gotta go from millimeter to centimeter, and then from centimeter to meter. So 10 millimeters is make 1 centimeter, so I had to divide by 10. And then 100 centimeters is make 1 meter, so I had to divide by 100. Altogether, I divide them by 1,000. You have any doubts there? Or you understand that question?
You understand?
All right. So Jonathan, divide 0.5 by 1,000.
Uh, 0.5 by 1,000.
0.5 divided by 1,000.
Oh,
Remember the amplitude was 0.5 millimeters.
0.0005.
0 point something like it.
000. 3 zeros.
So here
And
what?
then 5. Yeah.
Let me write it in standard form for them. So that'll
Oh, well then it would be 0.5 by 10 to the minus 3.
that'll be in standard form.
Oh,
You take the decimal and move it right before the first significant number. So I'm gonna
so
write
it'd be
out.
5 by 10 to the power minus 4.
Yes, meters. Right, and we have to figure out the period in seconds. Remind me, what's period that's wrong? Can I hear that's wrong? Jonathan, what is the period?
The period, there's time taken for one oscillation. So it'll be 2. No, no, no.
Not two.
It'll be 4. It'll be 4. It's
Yeah,
one oscillation. Yeah, it'll be 4.
Oh, and over here it is in milliseconds. So watch out, eh? So milli means to multiply by 10 to what power?
Oh, oh, to the I don't multiply seconds by 10. No, yeah, wait.
So milli, anytime you see milli, it means 10 to the power minus 3.
Oh,
Yeah, let me send you the charts. Nice. That you had to know. I might want to hear a fun fact.
Mm.
Or Jonathan, this goes for you too. People who are
huh?
people who are exceptional at maths apparently very complicated in relationships. Yeah, apparently. And it makes sense. Right, so Jonathan, that's you're supposed to remember. Milli just means by 10 to the power minus 3. And that's the answer there. 4 by 10 to the power minus 3s. Let me know if you're okay with that.
Yeah.
Right? You want to find frequency. What's the formula for frequency?
For frequency
Yeah, formula for frequency.
is F equals 1 over time.
Right? So that'll be equal to 1 all over 1 all over what?
4 by 10 to the power minus 3.
Right? So plug that into the calculator.
$250.
Yes, sir. And where's the units?
Good.
Jonathan, did I get all of that correct in the exam?
Yeah. I could have said the same.
I feel like this one I catch you know. I feel like I just right for. I have a feeling. What do you think?
Probably.
So let me just highlight that in bold. Right. Well, I didn't do electromagnetic waves in the crash courses yet. I'm gonna do that after we do these questions, but Jonathan, you should know one. Give me one property of EM waves. One property.
Electro electromagnetic waves.
All of them is travel at what?
At a constant speed.
Nah, it's a specific one.
Oh,
It's travel at the speed of
sound?
wait a minute.
No,
Jonathan,
wait.
wait. What is part of the EM wave, EM spectrum?
Light?
Wait, sir?
Light waves.
Light waves, right? And light waves just travel at what speed? The speed of light.
Yeah.
So, so all EM waves travel at the speed of light. Yeah. All EM waves travel at right? And all EM waves, they are what? Emma, what are they? They are transverse or longitudinal?
Transfers.
Yes. The only longitudinal wave is sound and seismic waves. Okay. That's right. Let me know if I was confused by anything I did there.
One question, all right?
Mm-hmm.
And number 3.
Yeah.
When it's in millisecond, I have to divide by 1,000.
You could do that, or you could just attach only 10 to the power minus 3. If you look at the chart, I sent some suffixes. It was suffixes or prefixes, I don't know. It was prefixes, yeah, prefixes that you were supposed to know. So check it out. So
Okay.
milli is milliseconds. That just means 4 by 10 to the power minus 3 seconds.
Okay.
Right? All right. Emma, wink, 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 wink. Mm. All right. So, Jonathan, how will you help me with this question here?
Yeah.
Is that-
Humans can see electromagnetic. Humans can see electromagnetic radiation only between the wavelengths of about 4 by 10 to the minus 7 m and 7 by 10 to the minus 7 m. This is what we call the visible part of the spectrum. A rattlesnake can detect EM radiation of frequency 3.5 by 10 to the power 14 hertz, and a honeybee can detect EM radiation of 1 by 10 to the power 15 hertz. Calculate the wavelengths corresponding to each frequency.
Okay, so Jonathan, we're not gonna get scared. We aren't. Let me show you how to analyze it, right? We're talking about what are we talking about in this question? Talking about, we're talking about
Talk about the electromagnetic radiation.
right, EM waves basically. All EM waves travel at what speed?
Speed of light.
Speed of light indeed. Right? Wait up. Emma. A serious son, Emma. Oh, good. Wait. How you get 113% efficient? What? You
That's wrong.
make a silly mistake there. First of all, hmm, the first rule for energy can neither be created nor destroyed, only converted. And the conservation of energy. Look at that. Think about it. If you're feeding the system, if you're feeding the system something, you can't get more on the output. Think about it.
Mm.
If if it have 0.17 amps in the actually in the secondary, like that's how much it's supposed to have, but instead it have 0.15. Is that a loss or a gain? Does it have more or does it have less? So in the first
It
question,
actually has less.
right? So it's like a profit and loss question. Is the profit over the original multiplied by 100, and then you add that? Or what you can do is you're gonna put you're supposed to put 0.15 over 0.17 because 0.17 is the original amount you're supposed to get. So you're trying to find what percentage of the original is 0.15. Yeah,
Oh, yeah, I understand. I thought this 0.15 was the original.
no. The or ideally, like a perfect transformer is supposed to have like 0.17. And if you get units, that's supposed to be 0.17 amps. An ideal transformer would have the 0.17. But they're saying over here it actually has 0.15. So I have a loss there. A loss in amperage. So you have to see how efficient it is. So I will check the others just now. After I finish. Right, so Jonathan. First things first, EM radiation. All EM waves travel at the speed of
The speed of light.
right? So then velocity is equal to
The speed of light.
right? And what's the speed of light?
3 point something. Did it forward?
3 by 10 to the power 8.
Yeah.
Where's the units?
MS. MS minus 1.
Correct. Now, here what going on, Jonathan? We have the velocity and we have the frequency. Do you know any formula that ties in velocity, frequency, and wavelengths?
Yeah. V equals F lambda.
So which one you want to find for first? The rattlesnake or the honeybee?
Rattlesnake.
First things first. Jonathan, we're trying to find for the wavelength, so I guess you can make that the subject of the formula first before you go and do anything, right? So how would I make the wavelength the subject of the formula? So we have to find.
Oh. Yeah, to move F to the other side.
So if we multiply by F, what we gonna do? We move it to the other side.
Yeah, be V over F.
So I would divide on both sides by F.
Yeah.
So lambda is equal to V over F. Okay, so we're gonna use that to figure out everything. So snake. So the wavelengths. Where's the velocity? So it detects an EM radiation at that frequency, but where's the velocity?
Radiation. The velocity is. Wait.
We're dealing with EM radiation.
Oh. The velocity is 3 by. Oh no. Wait. Yeah, 3 by 10 to the power 8 divided by 3.5 by 10 to the power 14.
It's a plug that into the calculator and let me know when you go. Yeah, Emma, that's the efficiency you're supposed to get. So if it was an ideal transformer, you're supposed to get 100% efficiency, but since you didn't get that, it's not ideal transformer because I had power losses.
Mm.
3 3 over 3.5714 0.28571 by 10 to the minus 27.
Nah, something wrong there.
Isn't 8.57142857 by 10 to the minus 27?
Nah, you're doing something wrong there. So it's exactly where you see you plugging it into the calculator.
Yeah.
Can I put it into my calculator then? Wait, you said 10 to the power minus 7?
10 to the power minus 7.
Because I heard you say 17. Let me show you why again.
I get 8. Hello?
Yeah? Tell me that's wrong.
I get 8.5714
Mm-hmm.
or 28. That's
Yeah,
one.
the same thing. Okay.
7.1
By 10 to the power minus 7.
minus 7, yeah.
Yeah, that was good.
Oh, I thought you would say 10 to the power minus 17. That's what I was
Oh,
told.
no.
Oh, okay. Well, yeah, correct then. So we go on the total 2dp. So our final answer is 8.57 by 10 to the power minus 7. And what is the unit for wavelength? Wavelength. Length.
Lambda?
Now, lambda is wavelength.
Is meters.
Meters. That's wrong. Wavelength. Length is measured in meters.
Okay, okay.
Yeah.
Yeah.
Lambda is just lambda just means wavelength. It just has a symbol to represent wavelength. But meters is the actual units. Right? So that's wrong. Help me find the wavelength for the honeybee now. So the honeybee is seeing EM radiation of 1 by 10 to the power 15 hertz. So we're dealing with honeybee now. So Jonathan, if you was doing this question, you think it'll make that connection with V is 3 by 10 to the power 8? Emma, you don't make that connection? I'm gonna take care of a while.
I would understood.
Okay. Because I saw a lot of people, they knew what the formula was, they just couldn't. They was like, what? What is velocity like?
Wouldn't they have given you at the end of the question too? Oh no.
They did. They did. They did. But you see, how much people go actually think make the connection there that the speed is 3 by 10 to the power 8. You understand?
Mm-hmm.
You gotta know, you had to understand that all the EM waves travel at the speed of light. You had to know that. Yeah. Right? So that's wrong. Tell me what to do.
With the honeybee?
Yeah, with the honey.
Okay. Honeybee can see electron segregation. Okay. Help us. And um when V equals
Now here what that's wrong. You could use our formula, but what we already do is we already make wavelength the subject of the formula. Because we wanted to find for wavelength. So we already find what wavelength is. If you want to find wavelength, that is the velocity over the frequency. Check it out. So that's wrong. Enter in this question, they're asking you for wavelengths.
yeah.
So I have V is equal to F lambda. That's the formula we're going to use. Now I
Yeah.
want to find for wavelength. So I will divide both sides by F. So lambda will be equal to V over F. You understand?
Yeah.
Right? So now any calculations I do, and I had to find wavelength, I will just use that formula. So my
Okay.
wavelength will be equal to what? What is the velocity?
I see him. Oh, velocity, uh, velocity is 3 by 10 to the power 8 over, um, over 4 by 10.
Hmm.
You have to add up the two?
What's that? No, we're dealing with the honeybee here. So the honeybee can detect EM radiation of 1 by 10 to the power 15.
Oh.
So we're dealing with the frequency that the honeybee could see. So for the rattlesnake, we
I
just
reading humans. What the hell?
now we're
My apologies.
dealing with the honeybees, man. Eh,
So
Emma,
1
Emma,
by 10,
yeah, it'll be 1
10
by
to the power 15.
right. So plug that into the calculator for now.
Yeah, so
If like bees was like puppy size, I feel like they would make real good pets. Because honeybee is so cute.
yeah, yeah.
Like they have it, they're so fluffy. They're so fluffy and small.
Until I kill you.
What? Where you come up with that boy? Oh my god. Honeybees, them real. I wouldn't describe honeybees as like vicious. Wasps. You talking about wasps? Are
3
we?
to the power 10 and minus 7.
That's right. You're talking about wasps and jeps. But bees chill.
People are allergic to honeybees.
That's right. You like honey.
Yeah.
Yeah, well, be grateful
Like
to.
the bee.
Oh my. Right. So Jonathan, you okay with this question?
Yeah.
So I'm just gonna pick you all up. Desron, anytime you see EM radiation, what is your velocity? All the EM waves is travel at
It's 3. That's not it. That's 3 by 10.
Hmm?
That's not it. 10 by the power of 8
Right.
milliseconds. I think so.
Now meters per second. Meters
Or
per second.
seconds.
Right. So all EM waves travel at the speed of light, guys. They travel at the speed of light. That's what we're on. Okay?
Yeah.
Cheyenne, if you're there, I want you to have more questions. See. Emma, you remember doing this question in test?
Yeah, I remember doing it.
Nice. I was on like course. Remember? And they come in hope and telling me what so what happened there in that question? Okay. Cheyenne, if you're there, see if we can have more questions. See. Emma, anybody else in class?
Maybe.
Okay, Cheyenne says she can't talk right now. Made her, I think you can have more questions. See?
Yeah.
So made her give questions. See, I read.
Thunders heard 2.3 seconds after a flash of lightning is seen. If the lightning strike is 750 meters away, calculate the speed for this event.
Okay, so you're seeing time and you're seeing distance. And they way to find speed. What for?
DST, so you get speed equals distance over time.
Right? Where's the distance?
750 meters. And 2.3 seconds.
Yes. So that'll be equal to
326.8.9.
326.9.
0.9.
Did you
you'll
say
get
0.09?
You get 0.09.
oh yeah, 0.09. 0.09.
Okay, so that'll just be 0.1 then. Wait a minute.
No, we round off 0.086 to 0.09.
Oh, okay. And where's the unit? Sounds like with speed.
Will be meters per second minus 1.
Now, if you say in meters, ms
Or
minus,
meters per second.
right. And that's it for
That
math.
slash is per.
Yeah, the slash is per, and the s minus one also means per. So ms minus one means meters per second.
Okay.
If you're saying ms minus one, it wouldn't say meters per second minus one. All right. And this speed is the speed at what? Tell me, girls, what's the speed? What's our speed for? Is the approximate speed of what?
Sound.
Yeah. What's the actual speed of sound?
330.
Yeah. Cool. Right. So we're gonna do these two questions. After that, we're gonna look at longitudinal transverse EM waves. After that, after we do questions like that, we're gonna look at refraction. Okay, we'll get 7 minutes break. We'll finish at like 7:30. Then we will move on to electronics. Right. And tomorrow we're gonna do two past papers. We're gonna do 2013 and 2017 to finish off. Okay, so Mira, cut more this question. Mira.
Carl and his friend Tommy were doing a school-based assignment on estimating the speed of sound in air using an echo method. Carl stands 100 meters from a wall. Carl claps two wooden blocks to produce a series of echoes, and Tommy, who is standing beside him, starts his stopwatch. After one echo, Tommy stops the watch. This process is repeated, and the time for 50 echoes was calculated to be 30.3 seconds. Calculate the speed of the sound generated.
Okay. First of all, Mira, if we are correct, we're supposed to get a value close to what? Since we didn't know speed of sound, what the answer is supposed to be close to?
Close to the speed of sound.
What is the speed of sound?
I don't know. Only speed of light.
That's all right. 300 to see.
Yeah, not to be.
Mhm. Somewhere around that. So Carl standing 100 meters from a wall, and he clapping two wooden blocks to produce a series of echoes. So after one echo, he stopped and he watch. So the process is repeated, and the time for 50 echoes was calculated to be 30.3. So here what made
You
her?
have to find the time for one echo first.
Yes, correct.
Well,
Right?
50 echoes to 30.3 seconds. So one echo would be 30.3 divided by 50.
That's right. Remember this morning how you had to do, you had to time 20 oscillations
Yeah.
and then divide. It's the same principle over here, same concept.
0.606 seconds.
What you get? 0.
0.606 seconds.
Right? And let me ask you a
And
question. So it one echo taking 0.606. Now for me that's what an echo is. So they're clapping the wooden blocks and what happening?
The sound will bounce back when you want to come back to them, so your distance will be a distance by 2.
Yeah. We have 100 meter. The sound traveling 100 meters to hit the wall, and then 100 meters to come back. So the total distance is actually 200 meters. So here what? We have the time, had the distance, how we find the speed. Speed is equal to what?
Distance over time.
Right? So it's
So,
up, right?
it'll be 200 meters over 0.6.6.
6.6 meter. Meter is something real sleepy. Real sleepy. Are you okay? You don't usually sound this sleepy.
No, and I wake up as I join class late. I go to school and I feel like I die.
Oh, you do any prayers?
Yeah.
How was your prayers?
Good.
Oh. So plug that into the calculator and tell me what you got.
330.033. Which is close enough.
No, that's extreme. Mira, the actual value is 330. And we get 330 basically. If you round it off to the nearest whole number, you get 330.
But don't they give you like the bottom of the question, like the speed of light and the speed of sound?
No, they just give you the speed of, they just give you the speed of light.
Ah.
You made how you will help me with this question here one time. So read part C.
A popular radio station broadcasts with a frequency of 100 by 10 to the power 6 hertz. Calculate in centimeters the wavelength of the sound waves generated.
Okay, Mira, before we do anything, radio station. Radio stations would emit what kind of waves? What kind of waves?
Radio waves.
And radio waves for those those waves fall on what spectrum?
Electromagnetic spectrum.
And anything on the EM spectrum had the speed of what?
Light.
Right. So that is why you see they're saying the speed of radio waves is that because it's an EM wave. So everything makes sense.
Mhm.
Right. All right, so we know what the frequency is. We know what the velocity is. How are we gonna figure out the wavelengths?
The wavelength is lambda, so lambda will be the velocity over the frequency.
Right.
So,
So
but
wait, for those who confuse, you write down the original formula. So V is equal to F lambda. So let's run. Let's run. You write down V is equal to F lambda. And I want to find for wavelength, let's run. I want to find for wavelength. So what I have to do on both sides? I want to find for wavelength.
You gotta divide.
I divided my what on both sides. What we gotta divide by to clear up by lambda. What we gotta do? What block in lambda?
Oh, I divide by F.
Correct. If I divide by F, the F and the F will cancel off and I'll leave us with lambda. You understand?
Yeah.
All right, so that's run lambda is equal to
So now it's V over F.
right. And what does lambda represent again?
Huh?
And what does lambda represent again? What's that? Which property in the wave does that represent? That's it.
Um,
That's your frequency.
A
That
wavelength.
wavelength. Nice. So made her tell me what to write. Where's my velocity? What's my velocity in this case?
Velocity is 3.0 by 10 to the power 8.
Right? And the frequency.
Frequency was, let's go up, 100 by 10 to the power 6.
Right? So plug that into
I got 3. I got 3.
like exactly.
Yeah.
What did you? And that'll be in what? What are we in?
3 meters.
Right, because we work with the SI units, didn't we?
Yeah.
Right? And any question, they wanted the answer in.
Centimeters.
So we
So
have
divide 3 by 100.
no. We're going from meters to centimeters. How much centimeters does it have in a meter?
100.
Right? So you wouldn't divide, you would multiply.
Oh yeah.
So copy that down. I'm coming back. All right, so made her. You're good with this, right? I don't know.
Yeah.
So we go with lenses, we go with V is equal to F lambda, them kind of thing. Let me just do a quick recap. Meter, when you're dealing with waves, where's the two kind of graphs you have to work with? Remind me. What the two graphs is work with?
Yeah, sine graph.
Yeah, there's how to work with displacement. It's how to work with displacement, distance graphs, and displacement time graphs. That's what it's how to work with. So check it out. So you how to work with displacement distance, and from those graphs, you can figure out the amplitude and the wavelength, right? The amplitude is the maximum displacement, the wavelength is the length for one full oscillation. So when you have a displacement distance graph, you can figure out your wavelength and your amplitude. When you have a displacement time graph, you can figure out the amplitude and your periodic time. So meter, the periodic time is the time it takes for one full oscillation. If you want to find your frequency, it's just 1 over the periodic time. The main formulas you need to know is V is equal to F lambda, S is equal to D over T. Right? And let me just write down some things to the side. Let's run. Once you're on the EM spectrum, what is your speed?
The speed,
Yeah, if you're on the EM spectrum,
it's 3 by 10. 3 by, 3 by, 3 by 10 to the power, 10 to the power of 8.
right? All waves on the EM
Just per
spectrum,
second.
right, travel at right, which is 3 by 10 to the power 8 meters per second. Okay, great. The next thing, the next things you all need to know. You all need to know how to differentiate between the meter like strong, how they differentiate. By the way, meter, I didn't forget the AdMaths crash course, so we still have some things to finish. I believe the exam is on the 17th. Is the 17th or wait, when is the exam? I made up. Just confirm with me.
I don't know, I write it down in my calendar, but I'm not home
It's
right now.
the 17th of May.
Okay, nice. Well, we have enough time. I had to do tricks, probability, and statistics.
Well, it will be ready made. Don't worry.
Made her
Get
put
one.
made her go and put on for there.
I don't think I
Get
that word
rude.
for physics, a word for maths. I have a bad feeling about it.
Add maths,
And my feelings always be true. Ask Varun.
add maths easy. Easy, boy. You'll be fine.
You get that one. Don't
Yeah.
worry yourself. You get that one.
Meta, don't worry. Add maths will be easy. Meta, just picking you up fast. With determinant. Sorry, not determinant, discriminant. What's the formula for discriminant?
B squared minus 4ac.
If the discriminant is less than 0, what does that say about the roots? Less than 0.
It is not real.
Imaginary, right?
Imaginary. Yeah.
Okay. If it is more than 0, I mean your roots are
Roots are real,
real and what?
and you have two distinct roots.
Right?
Rule. Yeah.
And what is it if it equals to 0?
You have one real root. Two equal roots.
You see, and you get worried for nothing. SMH. You'll be fine. Fine. Just call you know. Yeah. I think everybody will get one in physics, honestly. Physics not hard. Feel like everybody had a potential. Yeah. Okay, so let me look at transverse versus longitudinal. Okay, so Mira, give me any examples of a transverse wave. I'm gonna get a diagram on the board there. What's
Anyway, from the electromagnetic spectrum,
right? And what do we know about transverse waves? What is our specific property about them?
they all travel at the speed of light in a vacuum.
No? Mhm.
No, they all travel at the speed of light. What's the property for the Vern ringing on my phone?
Yeah.
What's the property of the one with the vacuum?
Wait, no. Mira, that you're correct, right? But not all transverse waves on the EM spectrum. You have other kind of transverse waves as well. An example of a transverse wave is if you move a slinky up and down. Desron, you know what's a slinky?
No.
I sure you know what's a slinky. I sure you know that.
Nah, don't.
That is like the spring kind of toy. You go see.
You what?
You go see. I'll share.
Hmm.
Varun class? Oh yeah, look Varun in class. I hear from Varun at all. Varun, you alright? Mira, what happened to Varun? What you do, the boy? Not hearing him at all.
Nothing. He wake up grumpy.
Oh. I feel like Varun is real coral, you know. I don't know, something about it. I just feel like it's real coral. But I feel like I know you just coral plenty. So like both of them just coral plenty, I feel. But anyways, let's run. This is what I'm talking about. This is our slinky. You ever see one of that before?
Oh, yeah.
Yeah. So let's run. Look at what's happening in a transverse wave. So look at it. If I'm moving this slinky up and down, right? I'm moving this slinky up and down. The movement of the energy, you notice it going in the opposite direction. It's perpendicular.
Yeah.
So I'm moving this slinky up and down, yet it's traveling straight. Right? So
Mhm.
that is an example of a transverse wave in action. Right?
Oh.
I'll give you a definition. Very nice definition. Right? In transverse waves, right? So that's one. Give that a read for me.
Huh?
That's one. Give that a read for me.
Good, what to read?
I say in this run.
No, not here, I'm looking.
Oh, well, you give it a read then.
Yeah, good what? In transverse wave, the displacement of particles is perpendicular to the propagation of the wave.
Right. So Jonathan, let me show you what I mean. So propagation means to initiate. So to move the slinky, you're moving the slinky in what direction? You're moving the slinky where? To propagate the wave.
Huh?
To propagate the wave. To start the wave off. I'm moving the
You have
slinky.
to you have to move it up and down.
Right? So this is on the X or Y axis.
Oh, this, yeah, I remember this.
So this is our movement on the Y axis. And this is and so you're propagating the wave by moving it up and down.
Yeah,
Now, the displacement of particles, so you see how the slinky moving up and down, that's what I mean by displacement of particles. It moving, right? It moving some distance. That is always perpendicular to the propagation of the wave. So look at the angle between the propagation and the movement of the energy. So there's transverse waves here. An example of transverse waves. Give me some examples of transverse waves, Jonathan.
Radio waves.
Yes. Now, truth be told, all EM waves are
Transverse.
Mhm.
Oh, okay.
So look at this again, right, Jonathan? I'm moving the spring up and down, so I'm propagating the spring, right? I'm moving it up and down, so I'm creating a wave. To propagate a wave means to create a wave. So by me moving the spring up and down, I'm creating a wave. But instead of the spring going up and down, the energy is transferred in the opposite direction, 90 degrees. Yeah, you understand that
Yeah.
concept?
Yeah.
right? And then we look at longitudinal waves now. I hear somebody in the background.
Huh? Wait,
I was hearing
oh,
something.
longitude, yeah. Longitude, I don't know. Yeah.
So the biggest example of longitudinal waves is speakers. Speakers is the biggest example of that.
Yeah.
Gonna draw a Batman speaker. Yeah, boy. Jonathan, you ever draw in your life? You ever draw before?
If I have, yeah.
Like,
Not like, okay. Speaker. Hmm. I don't have my ruler or anything, so I just gonna draw freehand. So I got the inner and this. I cannot draw top. This on top. Got this. So you got this one speaker. This is all on. Yeah.
I'm just not. Wow. I didn't know you're so good at drawing. That's very impressive.
No, it's just freehand, man. I could draw better if I had like a rule.
Hmm.
No, I used to do TD.
Oh, yeah, yeah. So I have a speaker over here, boy. Yo. Bam. I am an artist. Certified artist. Wow. Right? Okay, so Jonathan, you see this over here? That's the speaker. It's gonna move back and forth, back and forth. So, and by it moving back and forth, you're gonna push and pull particles. Some of them making sense.
Yeah.
And if it pushing and pulling particles and it displacing particles,
Yeah.
okay. Okay, so look at this. I want you to notice something. The propagation of waves is back and forth, and the transfer of energy is back and forth, back and forth. So the transfer of energy, you notice, is parallel. You notice the transfer of energy is parallel. You notice that?
Yeah.
When we put on the definition for longitudinal waves. So the displacement, so a speaker, let's move back and forth. So by doing that, it's displacing particles, right? So the displacement in long in longitudinal waves, the displacement of particles is parallel to the propagation of the wave. Right? And Jonathan, the biggest example of longitudinal waves is sound waves.
Sound waves.
Emma, I think you understand it a little better now.
Yeah.
Okay, nice. Anybody confused by transverse versus longitudinal. Let me know, guys. There's Ronnie confused by longitudinal versus transverse waves.
Um, not really. Not really.
Okay. So we know what longitudinal and transverse waves are, right? But also sound waves. Sound waves are also examples of mechanical waves. You're probably asking yourself, what is a mechanical wave? Well, a mechanical wave is just simply a wave that requires a medium to transfer energy. So, Jonathan, for you to hear sound, and the speaker has to move back and forth, and that would displace particles in the air, and that would hit your ears. Tell me if I'm right.
Yeah.
Now, isn't that a mechanical movement? It has to push and pull particles. So the medium there is air, right? If you put your head on a wooden desk and you hit it, it will displace particles on the wooden desk and you will hear it. The sound will travel through the desk. Do you think you could hear somebody in space?
No.
No, because there's no medium in a vacuum of space. So sound waves cannot be transferred because there are no particles to move back and forth.
Yeah, okay. I understand.
Right? And then we just look at the EM waves, guys. EM waves. So, Jonathan, what was the acronym?
The acronym for trans. Oh,
To remember the EM waves.
oh, LAM. No. No.
Rich men.
Yeah.
It was rich men in Vegas.
Oh, right, like the whole thing.
Mhm.
Yeah, I don't remember that.
Rich men in Vegas use X.
Use expensive with the I. Yeah, with the X, I mean. Expensive. Um, and so, well, let me try. Radio waves, microwaves, infrared.
Right?
V is visible, I think.
Yeah, he is visible.
U is ultrasound, X is I forgot, and G is gamma.
X is X-rays.
Oh, X is X-ray, right? And G is gamma.
Correcto. Right. Right, so we nearly finished with waves, guys. Nearly finished. Right, so Jonathan, rich, that means radio waves. Tell me one more time.
Microwaves,
Hmm?
infrared, visible, ultrasound,
No, that is
No, ultraviolet. It's ultraviolet.
yeah.
Yeah. X-rays and gamma rays. No, it would be so weird if you was able to see all the like everything from it.
You know, we can't even imagine that. Think about it. How can you imagine a color that you never
That
see?
do exist yet. Yeah.
Exactly. That's like telling a blind person, oh hey, you know what you just get when you mix red and
Yeah, no, you're
and
blind, but you gotta see this.
didn't even know what red and blue is. Bruh. And think about it, somebody who is completely blind, they don't even know that they're seeing black. That's
Oh yeah,
crazy.
true.
That's crazy to me. You know where's a mantis shrimp?
Oh, like the one those straw hands.
Yeah, yeah.
Yeah, yeah.
I believe they could see like 26 other colors.
Yeah, there's a lot of colors you can see.
So if those were like human size, we'd have be extinct by now. For sure.
Yeah, exactly. Because the speed they can able to like throw is very fast. You can't even see it most of the time.
Yeah, it's crazy. Right. So guys, which one has the highest frequency? Which one has the highest frequency? Is it a radio waves or gamma rays?
Which one? Oh,
Which one has the highest frequency? Is it radio waves or gamma rays?
would it be gamma?
The highest.
No,
Yes. Yeah.
wait.
Gamma is
Wait,
currently energy.
frequency is the one also. Yeah, it would be gamma. It would be gamma. I was mistaken for the amplitude on the actual frequency.
Right? So gamma has the highest frequency. They could ask this in the exam. Highest. Right? So it has the highest frequency. And let me show you something, right? V is equal to F lambda. If you make frequency the subject of the formula, frequency will be equal to V over lambda. So Jonathan, describe the relationship between frequency and wavelength to me. Look at the mathematical relationship. Is it
Is
is it proportional or inversely proportional?
inversely proportional.
Correct. Because when you increase your wavelength, since in the denominator, you will lower your frequency.
Frequency, yeah.
And if you have to increase your frequency, you have to lower down
You
the
have to lower your wavelength.
So with that being said, I'll leave that over here, right? I feel like that might benefit somebody when only revise them.
Uh,
V is equal to F lambda.
uh,
Frequency, that'll be equal to V over lambda. So then describe your relationship for me. Frequency is, come on, Jonathan, proportional, inversely proportional weights,
inverse.
right?
Wait, yeah, is inversely proportional.
It's inversely proportional. Right? So, so notes. So they could ask you something like this in the exam as well. So guys, according to the relationship to increase, so Jonathan, since wavelength is in the denominator, if I want to increase frequency, you'll have to do what's a wavelength,
If you want to increase frequency, you have to decrease the wavelength.
right? Right, and if I want to if I want to decrease frequency, well, let me not say like that. If I want to increase the wavelength,
You'd have to decrease the frequency.
right? Awesome. So here what? Jonathan, if gamma has the highest frequency, you think it also has the what? Think about it logical. If it had the highest frequency, it also have the
The lowest wavelength.
bang. Awesome. And radio waves. I think they have the what?
They have the lowest frequency and the highest wavelength.
Oh, Jonathan, I had to send you this video. A guy,
Uh,
he was working with a particle accelerator, and
and he had got stuck in it. Like half he had got stuck in it.
yeah, something like that.
Yeah, yeah, I watched that already. I saw a video about it, and the fish I guess stick in it. It not eating,
That's so
but
crazy.
it eating slower.
No,
Yeah,
no.
it is.
The one I was talking about was with his hand. His hand, he thought the machine was off, and he placed his hand in the
Oh,
particle accelerator, and electron beams passed through his hand, and like for a couple days, nothing happened, right? But as the days grew by, his whole hand grew tremendously in size, and it started to get blistered and red, and the skin started to fall apart. Like that's so crazy
oh
to me.
God.
That's so crazy to me. Like it's so small, but it's so deadly because
Yeah,
it come like guns that just ripping apart you at the molecular level.
remember the DNA.
And that's very scary because for a couple of days you'll think you're all right, but then as the days
And then after you wake up, your hand just falls. So
yeah, that's more dangerous than an actual bullet. Hmm.
yeah, cause with a bullet, right, you're able to get surgery and it get healed back. But
That's like permanent damage. And like when your
yeah,
cell replicates and thing, if your cells get damaged, it might replicate damaged ones.
yeah,
That's crazy. You know, people always thinking the bigger the better, but like if you wanna kill somebody, use 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 like very small bullets. You know? Yeah. Just shoot electron beams. Hmm.
yeah.
I'm gonna say that.
As if you want to kill them, like when you talk about the bigger the better, I think you're talking about how fast they want to kill them. Like, yeah, electro means it's deadly 100%, but it's take a couple of weeks.
Yeah, yeah. Took 30% to die. That's the only thing about it. Hmm. So we done with that. Nice. So that we do some questions. Hmm. And after this, we're gonna move on to Snell, which is what everybody here for. Okay. Oh yes, I have to do constructive and destructive interference. Mm-hmm. Yes. Do that one time. I think I should have this. It's like that was summary. Jonathan, you're right. I get shot by a real bullet or like by electron.
Where?
Your foot.
It's still bad. A real bullet, because it could get surgery,
I would say
and possibly TLAC.
I would say so.
You could go over Young's double split experiment.
Sure. Sure, I'll go over that. Right. So before I do that, I had to talk about constructive and destructive interference. So destructive interference. Emma, are you with us? Are you in the room with us?
Yeah.
You're nice. And you hear what we're talking about?
Mm-hmm.
You start with these. I feel like
Follow that. Mhm.
Emma, don't take this the wrong way, but I can imagine you, like, I don't know, if somebody piss you up, I can imagine you making like a electron gun and blasting them with it. I don't know. Imagine that. You like that. And like you would watch them suffer until they meet the inevitable death.
They're not that evil. In like maybe in my head I might think that, but Shweta might be the person to actually.
Emma would do that, trust me.
Nah, Emma would do that. Emma doesn't. I feel like Emma just think a lot of things on the inside. A lot of things she don't say. That's running
I
unmuted.
feel like that's about you too.
Me? Oh yes, yes, yes. I just think a lot of things. I'm like a mad scientist, you know. Cool. I think me and Han Verona just showed the shorts. You know, I feel like there's shorts.
Yeah, they do.
But like the people who like really, really bad, they don't show it. Yeah, they don't really show it. I just get the vibe from Shweta though. Like I feel like Shweta just tries to hide it, but she can't hide it. And I feel find like I could still pick up on it. Right? So Emma, tell me what amplitude you want me to have here?
I could say like 2.
Two, two. So Mira, you understand that these waves are in phase? Let me know if you understand what in phase means.
Yeah.
Right. They will ask you to describe Young's double slit experiment using this. So that's what it means to be in phase. Everything lines up. So, Mira, if I were to combine these two waves, what would my resultant wave be?
One exactly like that.
But what will the amplitude now be? See if you can tell me now.
4.
Yeah, the amplitude will now be 4. Because the two waves that were in phase, their amplitude would combine. And that's what has happened in Young double slit experiment. The light ray,
Shouldn't it be -2 at the bottom?
it should be. Excellent observation. Excellent. Sometimes our brain is be tweaking, guys.
That's okay.
Let me see what happened here. Well, what the hell? It just vanished? Eh, that's crazy.
Vanish or vanish.
What is it?
Vanish or vanish.
Vanish or vanish?
Spanish or vanish?
Spanish. Totally Spanish. Oh wait, I think I know what happened to it, you know. Wait. You get, how you get converted to a line? That's crazy. Emma, I feel like you could speak Spanish, you know? I think so.
I used to be able to. That's when we used to do it in form tree.
Oh, well, did you like that topic?
Yeah, that was probably my favorite subject.
No, oh God, I don't know you anymore. I don't know you anymore. Even
That
better now.
was back then. But I remember I told you I didn't like maths before.
God, you're wrong for that. Maths is king, right? So, whenever you have two waves that are in phase, meaning that the crest and the crest line up, the trough and the trough line up, you would have constructive interference and the total amplitude would change. So made her, if over here was 3 and over here was -3, what my new amplitude would that be?
5 and -5.
Yeah, correct. And let me just give you an example for destructive interference, and then I will do Young double slit experiments. Anybody else notice that the bottom one is a different color than the top one? Anybody else notice that?
Huh?
Emily,
Right now?
the bottom one is a darker shade of blue than the top one.
Huh?
As a very slight difference.
Yeah, I can't see that. Yeah, I will not see that.
Hmm. So, Jonathan, look at that. Are they in phase? Do they look
And they
like
will.
do they look like they are in phase?
They look like this directly opposite.
Right. So
Oh
if
no.
well, yeah, they're directly opposite. I just draw it kind of wonky, right? If they're
Oh,
directly opposite, they would cancel off each other. That's what would happen.
yeah.
Cancel off each other. So Mira, when you're doing Young's double slit experiments, where you have the dark fringes, that's where you have destructive, and that's what going on. So the waves just cancel off each other, and that's where you have a black zone. Right? Cool. Uh, Mira, you ready to do two past papers tomorrow?
2 past paper.
Yes, two past papers. Two past papers. We're doing 2017 and 2013. Yeah.
Okay.
Was speed. Right? Try to finish. We could try to finish our past paper in 1 hour and 30 minutes. I don't know how possible that is, but we go see. I try I think. Because it's take me 40 minutes or an hour to do a physics past paper by myself. The explaining will take longer. That will take long. Right. So Mira, see if you could come up with a definition for constructive interference.
Constructive interference is when the when two different waves align with each other, therefore making the amplitude twice the size, and
Well,
they're
it's be
when they're
twice.
both in phase,
It will always be twice and twice.
well, the amplitude, you add on the amplitude.
That is a perfect definition, you know, Meta. That's a perfect one. So see if you can call it all back for me again. If you remember.
I cannot remember what I now say.
Yeah, well, I will call it from the top of my head what I remember. So constructive So constructive interference occurs when two or more waves overlap and their amplitudes add together. Right? It's very important to note they must be in phase. Now, if two waves are in phase, then the crests and troughs have to align. Right, so Mira, you got to go with that, right?
Yeah.
Right.
Varun, why you so quiet? Talk now.
I wonder why he's so quiet. I'm really confused. Mira like a beady boy or something?
You should call him to do the next question.
Wait, what? A cinnamon roll could kill, no? I'm so confused by that, Emma. I mean,
Hello?
hey, look who has risen from the dead.
Yeah,
How are you? How are you, Varun? Yeah, he's back to the dead.
oh, really safe? No, but
How are you?
I did.
Made her fear anything?
Huh?
Made her threaten you or something? Like Galix?
No,
You get enough rest something?
no,
It's weird that it's so quiet today.
no, no, that's good.
Hmm.
I sleep for hour.
You went to
Well, you know, he was home all day today, and I told him make sure and sleep when I go to school, and he refused to sleep.
Hmm. Make sure and get sleep for tomorrow because you're doing two past papers, two whole past papers.
Yeah, yeah, no.
Where's it?
Yeah.
Nice.
So what time you might finish tomorrow? You finishing late tomorrow?
I finished 10 o'clock. Just
Alright.
Jonathan, just mentally prepare. Just mentally prepare.
And they prepare for what?
Tomorrow we're doing two whole past papers. I finished 10 o'clock.
1 o'clock.
No,
I don't mind finishing 1 o'clock.
Yeah. Jonathan will kill all you. Jonathan, how you feel about 1 o'clock, wait?
I better don't talk slow. I'm not gonna be there till 1 o'clock.
I doubt you go finish 1 o'clock. So destructive interference happens when two or more waves overlap in such a way that their amplitudes subtract from each other. Right? And this does happen when the crest of one aligns with the trough of the other. Right? So let me do Young's double slit experiment. Jonathan, do you know what Young's double slit experiment is?
What?
Young's double slit experiments.
Young dose with experiment.
Yeah.
Double slit. Oh, that's what this blasting like it's like very small particles through two slits, right?
Through what?
And it form like two slits in like a paper, and it form like in the background, yeah, and it form like 5 lines or something.
Yeah, I guess you could say that.
Yeah, yeah.
Okay, nice. Nice. It's got a nice diagram. It's got a nice diagram.
Hey, make draw a diagram.
No, I'm trying to look for a good diagram.
Oh,
Okay,
oh.
find a nice diagram. I'll send it on the chats. So that is what has happened. That is what has happened. That's a nice diagram showing what has actually happened. This is another nice diagram. So let me draw a diagram here. This is a bulb. I'm looking like a Pokeball. Right, so we have a bulb there, right? Basically, you can have any light source. And I'm gonna have a slit over here. Mira, what property of waves is this experiment exploiting? Is it refraction, reflection, diffraction, what it is? If you get on it.
Diffraction because it's going into a smaller opening.
Yes. The opening always had to be smaller than the water the wave. What?
Wavelength.
Yes. Right, so you have a light source over here, and the light source, it will have light waves come in. Okay, so Jonathan, for the fraction to happen, the size of the slits must be smaller than that of the wavelength. Show me the wavelength in this. What draw on the board there? Show me the wavelength for that.
The wavelength.
Yeah. Show me the wavelength of the wave I draw on the board.
It's small.
Show me measurements.
Oh. Like I don't like draw like a like draw something like this.
Nah.
Oh. What to draw then?
So this is the wavelength. I'll show you. Check it out. So this is the wavelength. That is the wavelength. So the slit has to be
Oh,
so for the fraction to happen and the Young double slit experiment to work, the size of the slit, it must be smaller than the wavelength. So must be smaller than the wavelength. Did you know that before?
no. I did not.
How you know? Right? So for the fraction to occur, the size of the slits must be smaller than the wavelength of the wave. You could ask this. Right? So anyways, let me draw the interference patterns I'm thinking here now. So surely we're gonna happen. So made I notice that some waves passing through, right?
Yeah.
Right. So it's over here where you will have the interference pattern. Let's copy and paste this. Right? And made if you had a sheet of paper over here, just draw a sheet of paper. So all the places where you have intersections. So like over here, all those will be bright parts here. So if you had light coming in, these the parts where you have intersections between the two waves, we call those bright fringes because those areas will be lit up. All the other regions will be dark. So Mira, I don't know if you understand that.
Yeah.
Why didn't you draw it in line like the other ones?
Wait, so
Cause like in this one you have the like light on the side of it, and then the other ones you just continue to like connect it like
I mean like this.
like how you have here and here not in line, but here and here in line. Does it matter?
I can feel that way, me. Hmm.
Like I was just watching how you drew it, how it would look on the page. So, cause this like shouldn't be like that, and you would remove this.
Oh wait, I see what you're talking about. See what you're talking about. So everywhere where it have an intersection, those will be the bright fringes, and everywhere in between will be dark. So like let's fix it. So wait, over here will be dark. Right? Hmm. So over here is bright, over here is dark. Hmm. Basically, it just had to show that. So like I feel like I'm overcomplicating it here. I'm gonna make it simpler. Just make it simpler. Basically, wherever you have the intersections, they're gonna be bright fringes. So I will send a diagram for you just now. So over here, that would be bright. Is what am I going? I'm gonna if you understand now. So over here will be dark, like so. Right? Over here will be dark, like so. Right? I'm gonna if you understand now.
Yeah.
Okay, nice. Right on over here. That will be light again. Wait, are you understand the diagram? I'm gonna if you understand.
Yeah.
Yeah.
It's on over here.
I know sometimes they use a screen as well instead of
Yeah, they do use our screen. Let me show you the one you're talking about. What's the one you're talking about?
yeah.
Same kind of thing. Same kind of thing. So that's young double space
I can
experiment.
back in 2 minutes.
All right. So Meta, if you want to be fancy, you could use these words. So you have bright fringes, bright fringes. Over here, the other ones are just called dark fringes. Right on Meta, at the bright fringes, what you have going on? That is what? Constructive or destructive interference?
The dark is destructive, the bright is constructive.
Yes. Right, so let me just give you something to write down. So interference atom forms due to The interference pattern formed due to the principle of superposition of waves. When light waves from the two slits overlap, they create regions of constructive interference, bright fringes, meaning that the waves were in phase as well as constructive interference. And these are the dark fringes. And this simply means that waves were out of phase. Interference patterns forms due to the principle of superposition of waves. When light waves from the two slits overlap, they create regions of constructive interference bright fringes, meaning that the waves were in phase, as well as destructive interference dark fringes, where the waves were out of phase. So mate, are you good with Young's double slit experiment now?
Yeah.
Mate, that was you? That sound like Emma just now.
Yeah.
Oh. So let me do some questions, and after this we can move on to refraction. Okay, cool. So, Meta, distinguish between transverse and longitudinal waves.
Could you repeat that?
So, we're doing this question here. A way to distinguish between transverse and longitudinal waves.
Transverse waves oscillate perpendicular to the wave. The transverse particle opposite perpendicular to the wave of the motion of the wave. Something like that.
Yeah, that could work. That could work.
And
So-
then the same thing but longitudinal particles oscillate parallel to the motion of the wave.
Right.
And it should include like refractions and compressions.
Wait, sir?
So you could include like in refractions and compressions for longitudinal waves.
Yeah, because for transverse, you have crests and troughs, and for longitudinal, instead, you have compressions and refractions. There's areas where the sound is compressed, and some areas where the sound is not compressed. Right, so the displacement of particles is perpendicular to direction. The displacement of particles is perpendicular to the propagation of the wave in transverse waves. However, in longitudinal waves, the displacement of particles
So what year is this?
2017. It looked like June. The displacement of particles is perpendicular to the propagation of the wave in transverse waves. However, in longitudinal wave, the displacement of particles is parallel. And it could also talk about the speed, right? Transverse waves, i.e. EM waves, travel at the speed of light, right? And longitudinal waves I dot E sound
You
Right.
need to include that in the answer too.
If you want, you can add it in. Yes. If you want, you could say. Right? Emma, give me one example of transverse waves.
A light wave.
Right. I just write visible light.
I could say a water wave.
You could say visible light, or you could say water waves, or you could say anything on the EM spectrum. Anything on right? And Jonathan, give me an example of longitudinal waves.
Longer. Oh, look at radio.
Nah, longitudinal waves are sound waves.
Oh, sound. Uh,
Remember, all EM waves, they are transverse, which is a nature. Just remember that. All EM waves, radio waves are EM
yeah.
waves, but transverse. Right? Okay, Neha, get this question I read for me. Made her. Chicken foot.
Ron, a Form 5 physics student, has available to him a brief filament light and array box, an opaque screen with two closely spaced narrow slits, and a large white screen. Describe how he can set up the apparatus to be able to observe an interference pattern of light and dark bands on the white screen and briefly explain why this pattern forms.
Okay. Oh. So let me show you how we're going to set up the experiment first, right? So you have the filament light. The filament light is denoted by the symbol over here. And in front of it, you're going to place the opaque screen. Now, the opaque screen, Meta, the opaque screen have what? What the opaque screen have in it?
They have two narrow slits.
Like so. And they have a large wide screen. Right? Feel like I should have brought the diagram on about what the diagram. Yeah, but it's just the whole diagram go look. It's a simple experiment, to be honest. Yeah, mira, so that's what this is what it could look like. So I just pretty definite, pretty explanation for you, like the lab setup. So mira, I feel like you're good to go with this question.
Yeah, good with this question.
Same moment. We're gonna live with that.
So we doing that paper tonight, sir?
What paper are we doing?
No, I was asking. Any people? Or they'll just go through like general questions.
Today we just going through general questions. We aren't doing a specific paper today. Tomorrow we're doing two past papers. Yeah. Right. So I'm just gonna give you the theory and we have to see for this question. All right, it fast. The first thing we have to see, place the right whatever. Yeah, you have to put it in our array box. Or the array box could be over here. Place a bright filament bulb in the array box. Step 2, place the opaque screen with the narrow slits in front of bulb. Right, so place the bright filament bulb in your array box. Place the opaque screen with the narrow slit in front of the bulb. And step 3, adjust step 3, position the bright screen front. So interference All right, nice. And the explanation for the bright and dark fringes is just basically this what they were right. Yeah. Simple as that. So that's how you get 6 marks for that question. Okay. So, Varun, help me with this question. Can I hear it, Varun? Jonathan, you want to help me with this question?
Sure. There's three types of electromagnetic waves in order of increasing wavelength. Identify the use of each of waves.
So, Max, that question, which one do you know has the biggest wavelength?
Radio waves.
Right? So we could start off with radio waves. And what after radio?
Trans.
So rich men,
Yeah, trans wave, right?
listen.
Radio waves and
So rich,
trans wave.
so rich men in Vegas. And
Oh, microwaves.
right, microwave. So we have radio, microwave, sorry, yeah, microwave. Right, what else?
Transverse wave.
No, transverse waves are the kind of waves
No.
that
Oh,
those are
no, not transverse.
so rich men,
Infrared.
yes, infrared. Yeah. So Jonathan, if you need to, write the acronym in the exam. Rich men in Vegas use expensive gadgets. Right? And where's our example of radios? Radio waves.
Radio, I guess.
Right? So you could say used to broadcast signals. Used to broadcast signals. And you can just put example on radio. Right? Microwaves. Used in microwaves to heat food. And give me an example of infrared.
Night vision goggles.
Is it?
No, that'd be infrared night vision goggles.
I'm not sure. I'm gonna check.
And this is infrared, right?
Vision goggles.
Oops.
Oh yes, yes. An example of as night vision goggles. The most frequent use of infrared rays is remotes. So Jonathan, the little light by a remote, on top of a remote, there's an infrared LED. You can't see it, but if you take your phone light and you put it and you take a video of you pressing your remote, you go see the light blink. You know that?
Yeah, it is. Remember in the physical class, you show me how you do that so you use your phone
Yeah,
and take
I think I remember. So Jonathan, look at that.
Hmm.
6 marks. 6 marks for that. Right? So the only questions we have to do now, we have to deal with Bruce. And we had to deal with this question. Okay, and that's it for waves.
I don't know what else after waves.
Well, I'll give all a 10 minutes break and we go start electronics. Yeah. We had a look at parallel series circuits. We had a look at V is equal to IR, the semiconductor diode, transformers. Yeah.
Re-
Varun?
yeah, mirror message man, they was calling. I went outside to get something.
Oh, you know, come back.
Yeah.
Oh, okay. Right. You're all about. Okay, so first things first, let's look at Snell's law. So we're going to do a refraction. So Jonathan, yesterday, remember how I was saying light does travel at different speeds and different mediums? Remember I was saying that yesterday?
Yeah.
Yeah. And we need to use Snell's law to describe that. So let me just put on the laws of refraction. I think that somewhere over here we start. Oh my. Yes. So Jonathan, give us a read here. These are the laws of refraction.
Yeah.
So I'll put like a more, how to say it? More detailed explanation. I'll say a more detailed explanation. So laws of refraction. Number one thing that I can't forget. The normal does exist what? The normal is always what? To the boundary line.
Right next to the boundary line.
Nah. The normal is always
No, it's the middle.
nah.
It's like
I'm looking for
huh?
perpendicular.
Uh
Yeah, the normal is always perpendicular.
to the boundary line.
Mhm. Right? Second one. So the second law of refraction I have to do with Snell's law. Right? And Snell's law describes how waves
And to have one the refracted ray, the incident ray, and the normal all lies on the same axis or something.
The angle, tell me this is what you're talking about. The angle of incidence and the angle of refraction lie on the opposite sides of the normal, but all lie on the same plane. That's what you're talking about.
Mm-hmm.
Yeah, that's one of the rules or the laws. Right, Snell's law describes how light waves bend when it passes through different mediums as light travels at different speeds. Snell's law describes how light waves bend when they pass through different mediums as light waves travel. As a result, light Right, Snell's law describes how light waves bend when they pass through different mediums as a result of light traveling at different speeds. Okay. I'll just leave it at that. And Snell's law, it is talk about the relationship between the angle of incidence and the angle of refraction. Right? The angle of incidence and the angle of fraction can be expressed as Ni, try this down, equal to Nr sine R. Right, so the normal is always perpendicular to the boundary line. Snell's law describes how light waves bend when they pass through different mediums as a result of light traveling at different speeds. The angle of incidence and the angle of refraction can be expressed as. That's two, now three. The angle of incidence and the angle of refraction lie on opposite sides of the normal dots. All lie on the same plane. Right. So laws of refraction. The normal is always perpendicular to the boundary line. Light waves bend when they pass through different mediums. This relationship own Snells law. Right. So those are the laws of refraction. Now, let me just go through refraction, right? So let me just say we have a boundary over here. So Meta, wait, pay attention. Let me just say we have, this is the boundary. Right, so Meta, over here we have A, and where you want over here to be.
Water.
Where would the normal be? Show me where the normal would be. Right. By the way, what's the refractive index in A? Do you know, Meta?
Is one.
Yes, because the Snell's law is based upon the speed of light in A, or in a vacuum, 3 by 10 to the power 8. So if we're talking about light in air, the ratio is just 1, right? So let me just say we have incident ray. Incident ray is just an incoming ray. That's so when you're describing what an incident ray is, you're talking about an incident ray is a ray of light that forms an angle with the normal and passes through the boundary line to go to another medium as an incident ray. It's an incoming ray. Right? So Meta, we have an incoming ray over here. This is the incoming ray. And I want you to show me what would happen to the refracted ray. So the angle is always formed between the normal and the incident ray, and is always formed between the refracted ray and the normal. So show me what the refracted ray would look like.
When it goes through a lighter medium to a denser medium, it bends towards the normal or away from the normal.
It bends towards the normal, I believe. Let me just double check. I will tell you. Okay, so if it's a denser medium, it goes towards the normal here. It goes towards the normal. If it's a less dense medium, it goes away from the normal. So I'll send you the table. Okay, so I'll send something on the chat. So let me just put a little note to the side. If you go into a denser medium, then your refracted ray, it would bend towards the normal. Right? So they could also axis. And if you go into a less dense medium, refracted ray, it would bend will bend away from the normal. So Meta, you good to go with that, right?
Yeah.
Okay, so which one then? Is that air or water?
Water.
Water. So you go bend towards the normal. So it might look something like that. And show me where's the angle of where's the refracted? Where's the angle of refraction? Where's the angle of refraction? The angle of refraction. Right, and you call that theta r. Right, and your refracted ray travels away from the normal. Cool. Let we discuss critical angle and thing now. So mate, are we gonna stick with the same example? The same example here. Okay, so mate, look how what's gonna happen as I go towards the critical angle. So mate, at the critical angle, what is the refractive? What is the angle of refraction?
90 degrees.
Right? So let me show you what that would look like. So Mira, look at this, right? You understand that if I make my angle bigger, it will bend more towards the normal, right? If I make
Yeah.
my bigger. So if I make my angle smaller, it would start to look like that. So I'm gonna show you how that would look like. And at the critical angle, your angle of refraction will be at the critical angle.
0.
Nah, at the critical angle, the angle of refraction is 90. So at the critical angle, so at the critical angle, the angle of refraction at critical angle, the angle of refraction is equal to 90 degrees. You understand? Made a if you
Yeah.
understand. I feel like it will make more sense if I draw the diagram coming from the other direction. So I'll do that. Let me show you what I mean by that. So okay, so Meta, let me switch up the scenario a little bit. Let me just say we're going from water to air, right? So Meta, we're going from, in this case, we're going from a what medium to a what medium? Less dense, more dense.
Less dense medium, the dense from medium.
So you're gonna move up, you're gonna move where?
Good. From air, the angle would move closer to the normal.
Nah. Since you're going from a less dense medium to a more dense medium, the angle of refraction will bend away from the normal. Watch. So if you go into a less dense medium, the refracted ray will bend away from the normal. You understand? So if you go into a denser medium, the refracted ray will bend closer towards the normal, but it will bend away from the normal. If you go into a less dense. Oh wait, I just now contradict myself. Because in this case, we're going from a Oh, well, no, I didn't contradict myself. Meter. Entry going from a more than star less dense. And air is less
We're
dense.
going from air to water, or water to air.
I'm going from water to air in this example.
Oh, well, it will bend away from the normal. I thought it was going from air to water.
Nah. You go understand it more if I'm going from water to air. Trust me. Because you do have total internal reflection and them kind of thing on air. You just have it under the water. See what I mean? So meter. That is the incident rate. And it go bend away from the normal length. That
Yeah.
would make sense, right? That make real sense. So let me ask that question. And at some point, if I make my angle of incidence big enough, and it will move so far away from the normal that it is now 90 degrees to the normal. Let me show you what I mean by that.
Yeah.
If I make that angle bigger, then what's gonna happen? This angle over here, it's gonna get closer and closer to B. And the point at which that happens, we call that the critical angle. So you understand the concept of the critical angle now, right?
Yeah.
We call this. So at this point, this will be a critical angle, and this over here, the angle of refraction, be 90 degrees. Emma, you understand what I'm doing so far?
Yeah.
You don't sound.
No, I understand.
I will erase this example. This example make more sense, a lot more sense. So Mira, if you're going from water to air, you're going from a more dense to a less dense, right? And water is more dense than air,
Yeah.
right? And Emma, we're going from water to air, right? So more dense to less dense. So if that's the case, your refracted ray will bend towards the medium or bend away.
It'll bend away from the normal.
Right. So if I increase my angle of incidence, look at what's gonna happen. If I increase this could bend further away from the normal. You understand?
Mm-hmm.
Sure you understand that, like 100%.
Yeah, I understand.
Jonathan, look at what I'm saying, right? Jonathan, if I were to take my angle of incidence and increase it, my refracted ray would bend, and it would bend even further away from the normal until it's 90 degrees to the boundary plane. Sorry, not the boundary plane, to the normal.
Hmm?
Yes, I'm getting confused. You want to explain that one more time?
No, I think I
Okay. So, Jonathan, if you're going from a more dense to a less dense, what has happened to the refracted ray?
is bend more.
It is bent up.
It's bend away from the normal.
Correct, bending away from the normal. So, Jonathan, I have an angle of incidence here. I'm traveling from water to air. From water to air. So, what angle will be bigger? This angle or this angle? Theta I or theta R?
The second angle.
Right,
VO1.
because it will bend away from the normal. So, Jonathan, if I were to increase this angle, will this angle get smaller or it would get bigger?
They get bigger.
It would get bigger. And eventually, if I make this angle big enough, and the line will reach until it's perpendicular to the
Yeah.
normal. And at that point, we call it the critical angle. You understand?
Yeah.
Oh, Lord. Right. Mate, are you okay with that? I just followed the definition.
Yeah.
As you increase the size of theta I, the refracted ray, well, yeah, the refracted ray will eventually so as you increase the size of theta I, the refracted ray will eventually bend so far until it is 90 degrees to the normal. So as you increase the size of theta I, the refracted ray will eventually bend so far until it is 90 degrees to the normal. Yeah. Okay. Right. Okay, and Midha, if I surpass the critical angle, so I go even further beyond the critical angle, what happened in there? See if you can figure that out.
You could repeat that?
So Midha, if I go even further and I pass the critical angle, what do you think will happen?
It will start going into the next medium,
Right, and then what will happen there?
and then reflection would take place.
Yes, that is what will happen. So Jonathan, you understand? If I increase the angle of incidence, and this thing will bend so far until it will just bend back into the other medium,
Yeah.
right? And at that point, you have total incident reflection. That's how it works. Emma, do you understand it clear as day?
Mm-hmm.
So eventually, it's so this over here, they will just call that the critical, that's the critical angle. Varun, Cheyenne, and Desron. And I hear another. I'm gonna probably confused.
Not really, to be honest.
Cheyenne, you okay?
Yeah.
All right. So Cheyenne, when you go in from a more dense to a less dense, the refracted radius do what?
90 degrees.
Wait, sir?
And it would be 90 degrees.
No, it is bend away from the normal.
Oh, okay.
Yeah. So Desron, look at this, right? If at the so at the critical angle, so you understand what happened, right? If you increase the angular incidence, the refracted ray will bend even further away from the normal until it's 90 degrees to the normal. You understand?
Yeah.
Right. So that's run. And all the time, we're going from water to air, watch, water to air. And there's
Mhm.
and over here, look at it. It's on the boundary line itself. So it kinda in air and it kinda in water. Now there's run. Let me just say, I increase the angular incidence even more. And this thing will get pushed down even further away from the normal.
Yeah.
So look at what happened there. So now we're going from water to what?
Water.
Water to water. And at that point, you have total internal reflection, meaning that it being reflected. You understand? So it have like a reflection. So check it out. So this angle over here, theta I, that would be equal to this angle over here, theta R.
Okay.
So me that you understand the concept fully there. Let me know if you have anything that confusing here. If you go past So eventually the refracted.
Rajiv, we have plenty more to do because I have to leave just now.
Oh, okay. Well, I wouldn't be able to do electronics today then. Tomorrow will really be a long day, yes. Oof. Hey, what? I will stop at the two questions. I'll stop at the two questions. Emma, you could try the electronic questions and I'll tell you if it's correct, right? I mean, I think you sent it to me already.
I did the one for 2013 and I did the one for 2017.
Nice. And
I don't think what I did for 2017 was correct, but that's right.
I will check it. So, Meetha, let me just run over the basics, right? Before you go on thing. So, Meetha, if I go in from a more dense to a less dense, what going on? Okay, on the hand, Meetha, who wants to do the live demonstration with me? Just to go it over again one more time. All right, Shannon. So if you go in from water, and this is a kind of harder example, you're going from water to air. First of all, you have to show me what the normal is. Show me what the normal is. The normal is always what to the boundary line.
Perpendicular.
Right. So show me what the normal is.
Nobody.
Yeah, that's correct. Right, so Cheyenne, if you're going from water to air, water is more dense on air or less dense on air?
More than.
More dense. So you're going from a more to a less, right?
Yeah, so the refracted ray can bend away.
Yes. So more dense, less dense. Refracted ray will bend away from normal. So Cheyenne, let me just say let me just say this. Wait. Yeah. So show me what the angle of incidence is. I'm going from water to air. Show me what the angle of incidence is.
Over here.
All you think that's correct? Jonathan, you think that's correct? Cheyenne saying the angle of incidence is over there.
The angle as well.
She's saying that the angle of incidence is over.
Is one.
She's saying that the angle of incidence is over here.
Usually we give you any different side, next side.
Yes.
is.
It will be over here. Cheyenne, you're always forming the angle between the ray and the normal. Always. Always. So that will be your angle of incidence, right? So Cheyenne, show me the refracted ray now. You're going from a more dense to a less dense, so you go bend away from the normal. So
Oh god.
yeah, that'll work. I will take that. Right, that's not so bad. And so Varun, if I increase my angle of incidence a little more, what do you think will happen?
If you increase the angle of incidence, you will create a critical angle.
Yes.
Yeah, 90 degrees.
Perfect. So Cheyenne, my refracted ray will be my angle of refraction, that'll be over there. As I see you figure that out.
Yeah.
Nice. So Cheyenne, look at what's gonna happen, right? if I take the same diagram and I increase the angle of incidence, this will get pushed even closer to the normal, to not even to the boundary line, right? And if and if I go even beyond that, they're gonna come back into the own medium. So now we're gonna be going from water to water, and at that point, you're gonna have what?
Critical angle.
Nah, that is total internal refraction. Sorry, reflection. Yeah.
Okay.
All right.
Critical internal reflection. Okay.
So over here, in the first situation, you have any critical angle or anything, or that's just incident and refracted?
Incidental refracted.
Right. So let me take the angle of incidence and increase it. That's what we're gonna do. That's the plan. If I increase it to over there, first of all, show me where the angle of incidence is. Show me where the angle of incidence is.
Over there.
Right. Show me how the refracted ray gonna look like now.
It can be closer to that, of course.
Yes, that's perfect. So let me just call this the critical angle, right? Why not?
Yeah.
Just to make our lives simple. So Varun, you understand that?
Yeah.
Nice. So Shayan, show me the angle, show me the angle of refraction. Show me the angle of refraction,
Over there.
right? And that will be how much degrees?
Like,
Yes. Yes. Right? So Shayan, here it is, right? So Shayan, at this point, when the angle of an incidence causing an angle of wait, huh? No, phrase what I'm saying properly. So Shayan, this particular angle of incidence, and it caused the refracted ray to be perpendicular to the normal, 90 degrees. So we would call this the critical angle. At the critical angle, the angle of refraction is
90 degrees.
right. And the third scenario, right? If I take the same diagram and increase the angle of incidence there, what's gonna happen? They would just say
Total internal reflection.
perfect. So now this, what going on there? Oh Lord, pressure in the camp. But get to not draw back a line, but oh well. Oh God, we have
Oh, Lord.
right. So Cheyenne, in this over here now, it going from water to air or water to water.
Water to water.
Right. And since that is the case, you have total internal reflection.
Yep.
So this angle over here, is it less than the critical angle or more than the critical angle?
More than the critical angle.
Right. Right. And show me the angle of refraction. Well, in this case, it will be angle of reflection.
It could be over here.
Yes. Awesome. Awesome. Right. And in this diagram, you're going from water to water. And this is total internal reflection. Awesome, guys. So Varun, you ready for them now? Varun? Yeah, I see a drawing with a second line. Okay. Okay, cool. So now let us look at the main formulas you need to remember. Main formulas you need to remember. And we will do some questions now. The number one formula you need to know. You need to know that Ni sin I is equal to Nr sin R. Right? Ni, that's the refractive index. That's a refractive index for the respective medium. And R is the same thing. Okay, and a couple of refractive indexes you need to know. Cheyenne, what's your refractive index at A?
1.
Right. Refractive index of A. That is equal to 1. And sometimes it is expected to know the refractive index of glass. Glass. Emma, just confirm the refractive index of glass, and it was 1.5.
Yeah.
Right. Okay, and I have a formula to remember. The formula don't come often, but it does come. Since I need to know it. Right? Okay, one second. To know that formula, and this is the other formula you need to know. What was the formula though? I'll tell you just one. One second. Just reply to a message here. It's identical. Okay, so you need to know Snell's law. The other formula you need to know. It comes really, but it still come. N is equal to the speed of light in air all over speed of light in the medium. So Jonathan, I think I explained this to you, right? And light is travel at different speeds depending on what the medium is.
Yeah.
So the refractive index is just a ratio between the speed of light in air and the speed of light in another medium. Yeah, that's what the refractive index is. So you need to know these two formulas for sure. Right, so now that we have everything in action, we can do some past paper questions. We're just going to do two past paper questions. Right, so you all might want to copy this down. These are the two formulas you need to know. Hey Cheyenne, you hear Ravi be losing dog?
Yeah, we was talking about that in school today.
He find back dog though.
Oh my lord.
He dog real cute.
This formula is in the document, yes, sir?
Let me check. This is something you're supposed to know, for refractive index. That's what refractive index means. But I'll check it. Let me see if it's in the documents.
Chief,
Yeah, it's in the documents
Alright.
of all these formulas.
Chief.
Yeah, that's wrong.
Alright. One question, right?
Yeah.
Oh, I was doing before, right? We're going from water to light. I mean, right. Water to air.
Mhm.
And moving away from the normal.
Yes. So
Okay.
as you increase the angle of incidence, it goes even
Yeah.
further away from the normal. And you're always
Okay.
measuring it. And the normal is always perpendicular to the boundary plane. It's always perpendicular. Always.
Okay.
So you're good to go with that, right? That's wrong.
Yeah.
So when you all have this copy down, let me know. We'll start the past paper jamming. Jonathan, just let me know if you're okay. Let me know if you're all right with everything we're doing so far.
Yeah.
Some additional formulas that if you want to know, you could know. I'll write it down for you. So the refractive index, that's also the same thing as the wavelength in air all over the wavelength in the medium. Right, so I made her on Varun and the rest of you guys. When you all have everything copied down here, well, let me know. All right, let's move on to the questions. No mercy. Emma, you understand everything we did so far?
Yeah.
Straight into the pits of fire. Sorry, pits of hell. Okay, all right. Let's go. Who wants to help me with this question? I just have two questions. So,
Runilal.
Varun, okay. Varun, get this question, Ari.
Why is that?
Runilal, where are you?
Not sure what
Varun lost. You have to put up a missing poster for he now. He and Rafi dog run away together.
I feel so, you know. I feel so. But Ravi, we find the dog. Let's see, Ravi, we find the dog.
Runilal.
He probably pick up Varun too.
Probably.
Hello.
Hello?
Fine.
Oh, hello.
Yes, Varun, help me with this question here. And Emma, you can just follow along carefully, right? If anything confusing, you go along.
Yeah.
The other question is even harder than this one. So Jonathan, you will help me with that one. I just want to make sure you understand. Because I know this topic is here, some trouble. Yeah. All right. So Varun, get the question already.
Figure 2 shows a narrow beam of white light which is shone onto a triangular prism at an angle of incidence of 30 degrees. If the angle of refraction of the violet light is the
If the angle of refraction for the violet light, theta v,
theta v is 20 degrees, what is the refractive index of this prism for the violet light?
all right, Varun. So first things first, you're going from where to where? Where are you going from?
The angle of violet light.
You're going
Oh, from
where's that?
here to here.
Right on all over here. Where's that? That is water, that air.
Air to glass.
Yeah, you're basically going from air to glass. Which one more dense?
Glass.
So you're going from a less dense to a more dense.
So that means the um refractive rate will bend towards the normal.
Correct. And that makes sense because look at that. The angle of refraction is 20 degrees and the angle of incidence is 30. You see what happened there? It bent towards the normal.
Yeah.
All right. So I'm gonna show you this formula because you can use it anywhere you want. So Ni sin I is equal to Nr sin R. So Varun, Ni is just the refractive index of air. Wait, let's write the formula here. Ni sin I. All right, so Varun, the angle of incidence here, and the angle of refraction here, right? The angle of incidence is where? Is it in air or glass?
Angle of incidence.
Yeah, that's in air or glass.
Air.
Air, so your refractive index will be what? What's your refractive index at air,
1.
right? And where's the angle of incidence?
30 degrees.
Right? So we go write 1 by sine 30. And do we know what the refractive index of the glass is?
No.
So we leave it now blank. And do we know what the refractive angle of refraction is?
Yeah, 20 degrees.
20. So Varun, if I want to make NR the subject of the formula, what is one more?
You divide by sin r on both sides.
Where's them?
You divide by sin r on both sides.
Divide by sine. Sine what's on both sides?
R?
Nah. If you want to find from N and R, so we're trying to find for NR. This whole thing you're trying to find for. So I would divide by sine 20 on both sides.
Oh, wait, no, I was referring to the formula up here. So that was it, you get divide by sine
Oh.
R on both sides.
Okay, okay. Well, that makes sense. That makes sense then, right? So 1 by sine 30, that's just sine 30. So you're really plugging in sine 30 over sine 20. And tell me what you get. Make sure you get it in degrees, not gradients, like last time.
No, I get it. 1 point, you wanted to round it off to how much? 2 decimal places?
Yeah.
1.46.
And the actual refractive index for glass is like 1.5. So like we close enough, right?
Yeah.
Right.
So,
You confused by how I do that question?
no, I get it.
All right. So, Jonathan, you understand what I do there?
Yeah.
Cheyenne, you okay?
Yeah.
Mita, are you okay? Emma, are you okay? What's all you okay?
Yeah.
Yeah.
All right. The next
Yeah.
part. Desron, you all right?
Not really. Just the NI. I see NI and the NR.
Rajiv,
Everyone?
what year is this?
I don't know. I genuinely don't know. I can't tell.
Okay.
Yeah. So Desron,
Yeah.
NI, that's the refractive index from where you're starting at. And NR is the refractive index of where you're going to. So Desron, you're starting off in A, right?
Yeah.
The refractive index in A is 1. So Ni, that is just 1. That is what it is. And Nr, that's the refractive index for the glass, because that's where you're going to.
Okay.
So it's again, Ni, that's the refractive index for where you starting off. So we start
Yeah.
off here. So the refractive index for air is 1, and we go into glass. So
Okay.
that NR representing the refractive index for glass. So I'm trying to find fit. So I divide by sine 20 on both sides to cancel off. So I remain with NR. So NR is just sine 30 over sine 20. Understand?
Yeah.
All right. Nice. So Varun, give part 2 a read. Varunilal. Isha, you see the video where Trinity introduced his son?
Yes.
Oh,
That name was crazy.
yeah, boy. See Takaran. Not here, and Varun.
Yeah.
All right. So Varun, read part 2 for a minute.
Calculate the speed of the violet light in the prism.
Hey. Varun, you got to handle it skillfully. You're going to handle it skillfully, right?
Yeah, sure.
So, Varun, which formula we had to use for this? I gave you some formulas that I had to remember. So which ones does have velocity or speed in it?
This n equals the speed of, no, wait.
Yeah, you're going good.
N equals the speed of light in air over the speed of light in the medium.
Right. So, Varun, violet light, and that's visible light,
Yeah.
and that is in what spectrum? That's a what kind of wave?
Electromagnetic.
And all electromagnetic waves travel at what speed?
Three by 10 to the power 8.
So the speed of light. Yeah.
Yeah.
So you notice that is why I gave the speed of light here. So, Varun, think about it. Put everything together. We just not find a refractive index, right? So, what is the refractive index of the glass?
1 point. Oh, the refractive index of glass. Oh yeah, 1.46.
Right? So that's wrong. That 1.46, right? That stood for the refractive index for the refractive, sorry. That's the, gosh. I feel like my brain bust there. So that's wrong. As a refractive index, right? For over here inside the glass. You understand?
Yeah.
So in the next part, they're asking you to find the speed of the violet light in the prism. So that's wrong. You think light gonna travel the same speed in air as opposed to glass?
No.
Nah. And to go how to think about it. You could run the same speed in water as opposed to land?
No.
Nah. So by going to a different medium, the speed will be affected. Right? And there's a formula you're gonna use for that. N is equal to speed of light in air over the speed of light in a medium. So that's run. In the previous part, we found the refractive index for the prism, the glass prism, and that was 1.46. So I'm gonna plug that in over here. You understand?
Yeah.
All right, and Varun, what's the speed of light in air?
3 by 10 to the power 8.
Right, and that'll be over the what?
Speed of light in a medium.
Right, because we don't know what that is. We don't know how fast the light traveling in the glass. Right. Yeah. Varun, what will we do there?
Cross multiply.
Cross multiply, is it?
Yeah.
Yeah. I feel it hard to write all of this, so I just go and call it VM. Right, that just means you
Yeah.
don't you need to
Two.
be. Yeah. So that's right, you can call it anything you want. Really? Call it anything you want. So I just can't call it VM. That just means
Yeah, Vernon and Midland.
I didn't think about it like that, but yeah, that makes sense. Right? So what we're gonna do next?
So you're gonna cross multiply the VM multiplied by 1.6. 1.46 equals 3 by 10 to the power 8. And you divide by 1.46 on both sides. So then you will VM equals 3 multiplied by, until you divide by, yeah. Come on.
Wait, Varun, before you do anything, you think you're traveling faster in air or in the glass?
In air,
Yes. That's run because aren't you just run faster in air than in water?
Yeah.
So that's run. What I'm trying to say is the denser the medium, the slower it will travel. You understand?
Yeah.
you get a very big number.
Well, Varun, the original speed was 3 by 10 to the power 8, so we're expecting a big number, but something less than. Again, wait, you have a Casio?
Uh-huh.
You're supposed to get it on a standard phone already.
And again, it doesn't have the phone. Again, it doesn't have the phone.
Press ENG.
Yeah, that's what do.
Oh no, ENG wouldn't give you to the degree you want. So you can do it one way.
Uh,
So Varun, call it out for me.
2054 79 452.1.
Oh boy. So we're gonna write our answer in standard form. Now, if you write in the answer in standard form, you're gonna shift the decimal place right
So
before
you-
the first significant number, which is 2. So 1, 2, 3, 4, 5, 6, 7, 8. Since I shifted it 8 spaces to the left, I'd multiply by 10 to what?
10 to the power minus 8.
No.
Oh. Oh, wait, it's 8. It's 8.
Mhm. That would be 2.054794
Oh,
5.
Verna, you can get on your calculator, you just have to press shift setup, I think, and you will see normal, fixed, and standard. I'm here to go on standard.
Right, and there's one. What we just measure velocity in?
Huh?
There's one. What we just measure velocity in?
Velocity?
Yeah, velocity is the same thing as speed. What we just measure that?
Yes. But what's no one? Velocity is meters per second.
Yes. So there's one. Was our predictions correct? Does it travel faster in the glass or slower?
So go
Look at it. So in the
slow.
right, because in air it was 3 by 10 to the 8. Now in glass it's 2 by 10 to the 8.
Yeah.
That's wrong. How you feeling about that? You understand?
Yeah.
All right, so that's wrong. Now I help me with the last question. Right, so really last question from there.
All right. Calculate. Calculate. Hello?
Yes.
Yeah, listening.
Oh. Okay, the frequency of violet light in the wavelength in the air.
That's
Like
simple.
40 centimeters. No?
That is
Meters?
nanometers. Nanometers.
Okay, nanometers.
And look what it's saying over here. 1 nanometer is equal to 10 to the power minus 9 meters.
Yeah.
Right? So that's wrong. What formula you know? Have frequency, wavelength, and something else in it. What formula?
Let's see. Wavelength. Frequency, wavelengths. IV equals F lambda. What do we call it?
Oh boy. Yes. That's what we're talking about. And you're trying to find for what?
You're trying to find frequency.
So how to make frequency the subject of the formula then?
You have to
Wait, sir.
you have to divide by
Yeah, it was going good.
yeah, divide by lambda. Or lambda, what we call it.
You were saying it good. Imagine somebody said Lamborghini. Oh, somebody said Lamborghini. That's right. When you become on here, say buy a Lamborghini.
Nah,
Hmm.
our Benz.
Oh boy. What are we talking about?
So I have a question for the last part.
Yeah. Yeah.
So I saw that you said n is equal to the speed of light in air over the speed of light in the medium. Does it depend on where it actually going if you're using this formula? So if it was, so say in this case it's air to the medium, you'll use air over the medium, but if it was the medium to air, it would be the medium over air.
Nah, this is the refractive index is always measured this way. Always. It don't ever change. This is what the refractive index means.
Okay, I understand.
So, Emma, the refractive index is just simply the ratio between the speed of light in air over the speed of light in any medium. That don't ever change. So anytime you get a refractive index or something, that is what it's measuring. Is a ratio between the speed of light in air to the speed of light in the medium. That is why the refractive index for speed of light in air is 1. That is why. Yeah. So that don't ever change. The refractive index is always this. Mhm.
If that's a note of that.
Okay.
I mean, I remember, but just in case.
No problem.
Reggie, by chance you have a blank document in there?
What do you mean? Like, with the
Just
questions?
out the writing, that's the question.
Yeah. You want to send it?
Yeah.
Okay, no problem. Please
I
remind,
want to print it and try them back myself as we do it already.
please remind me. I'm very forgetful. After class, I'll go knock out. Yeah. Just remind me on the chat now. Or just private message me. Right? So the refractive index is always the ratio between speed in light over speed in another medium. Yeah. Right? So that's run. F is equal to V over lambda. And
Yeah. Yeah.
run. Tell me, where is the velocity at the light? So they was talking about violet light. Where is the velocity for that?
Is it's not 3 to the power. It's 3 by 10.
10 to
Right?
the- 3 by 10 to the power
3
8.
power 8.
Yeah.
Yeah.
So that's run. Anything that fall on the EM spectrum at the speed of light. And look at what it is. It's giving hints over here as well. So look out for that. So anytime it dealing with light, no matter what color the light is, all light travel at the same speed. All EM waves travel at the same speed. Don't forget
Yeah.
that. So that'll be 3 by 10 to the power 8. And what's the wavelength?
Wavelength is wavelength is 430 nanometers.
Would I leave it as nanometers or would I have to convert it to the SI unit?
That's a converted to the SI unit.
And how am I doing now? Tell me.
Reggie, but if we now found for the velocity, why are we not using the velocity of the violet light that we now found? Oh, wait. Don't worry, I realized because that was in air.
Yeah.
That was in okay.
430.
Mhm. And what does
I divide.
what does nanometer? What does nanometer stand for? They're telling it right there. What does nanometer stand for?
Oh. It's smaller. 1 nanometer is 10
10 to the power.
power 9 meters. Yeah.
Right. So let's run. Check what I said on the chat. I'll point it to you. So the prefix thing there, the prefix. So nano just means to multiply by 10 to the power. Well, they don't have nano in the one I said. That is why
Yeah.
they about it. But the prefix just means you have to multiply. So let me just say it was megameter. You had to multiply it by 10 to the power 6. If it was micrometer, you would multiply by 10 to the power minus 6. But since it is nanometer, you're multiplying by 10 to the power minus 9. Let me know if you understand that.
Yeah.
It's 430 multiplied by 10 to the power minus 9. And that's exactly what you're going to put in the denominator. Right, so wait, it was 430, I mean. Right, so plug that into the calculator and let me know how things running out, how things looking out.
Yeah, I'm not sure what it is. I got 4.3. Or 10 to the power minus 7.
Nah, that wrong. By plugging it back into the calculator. Don't forget it's minus 9, to the power minus 9. By chance you put in 10 to the power 9?
No,
Hmm.
that's no. Don't do too bad.
Somebody could cross try it.
I got 6.976744186 by 10 to
know
the
that
power
too.
14.
Right, so round up that to 2dp and you'll get 6.98. Right, by 10 to the power 17. And that's wrong is a unit for hertz. Oh gosh, I see it. The answer is hertz. Oh gosh, I'm sorry. My brain is autocorrect sometimes. I don't understand. I don't understand how that work. Yeah, so that's wrong. Frequency is measured in hertz. Don't forget that. Don't forget units.
Yeah.
Units is literally like a whole mark. Whole mark for that. So that's wrong. You're feeling okay?
Yeah.
Nice. All right. So, Jonathan, get this question I read.
State the laws of refraction.
Okay, well, I wouldn't bother to go through that because it's already in the documents. That'll waste time if we had to write that. But basically,
Yeah.
these are the laws of refraction. Where are they? The normal is always perpendicular to the boundary line. Light waves bend when they pass through different mediums as a result of light traveling at different speeds. This relationship is known as Snell's law, as shown below. The angle of incidence and the angle of refraction can be expressed as Ni sin I is equal to Nr sin I. That's Snell's law. And you had to say the angle of incidence and the angle of refraction lie on opposite sides of the normal, but all lie on the same plane. That's the laws of refraction that I need to know. Yeah, so I wouldn't waste time on that. Yeah, this is what we're interested in. This was one of the harder questions. So Jonathan, read part B.
Figure 3 shows the clownfish Nemo looking at point B. It sees the fisherman's net appearing as if it were at A. Calculate angle C given that angle ABD is 42 degrees.
Yeah. So Jonathan, you feeling cooked?
If you will,
If you're feeling cooked,
kinda.
nah, don't feel cooked. You're ready for them. You're ready. So let me just run through the question. So figure 3 shows a clownfish Nemo looking at point B. Right? It sees the fisherman's net appearing as if it were A. So Jonathan, the draw the diagrams kind of stupid here to confuse you. But if the fish
Yeah, what's CP40?
Wait, sir?
Would C be 48?
Yeah, C is 48,
Okay.
right? But Jonathan, if Nemo looking up, he really going from, and he really going the opposite direction. Think
Yeah.
about it. Really going the opposite direction, to be honest. Yeah. So the first part, calculate angle C, given that angle ABD is 42 degrees. Okay. Now, Jonathan, BD, that's your what? B to D, that's what? Come. That's your what line?
B to D.
Yeah.
Does he? No. It's the a flat line. The one a perpendicular to the normal.
So that is your boundary line,
Yeah, boundary.
right? Just label and everything. So this is your boundary line. This over here, this is your normal. Cool, cool. And they want you to calculate C, given that angle ABD is 42 degrees. So Jonathan, this over here, that's our what? What's this? That red thing I just saw draw. Don't overthink it. You get the correct
Is a
answer.
line.
Is a line, right? There's Ron, if you have a line, what is the sum of angles on a line? Maths. What's the sum of angle on a line? On a line?
180?
180. So that's Ron. This whole thing is 180.
Yeah.
Now that's Ron. Over here, have the, what you just call this line over here? This is what? The red line. This over here.
In,
You will see it just now. That's the what?
in normal?
That's the normal. Excellent. So this over here is your normal. And this blue line, that's it. What was the blue line?
I the what kind of name now?
So over here, this is A,
A boundary line. Okay.
right? That's a boundary line. So the normal and the boundary line is always what?
Oh, it's what would I what
What angle is looking like?
90
Yeah, perpendicular.
perpendicular, yes.
So made her, if this is 90 degrees and this is 42 degrees, right? Figure out what this could be. Teamwork here.
48.
Right. To figure out that was 180 degrees minus 90. That's 42. Jonathan, I want you to notice something, eh? C is the what angle? What angle is C? That's the what angle?
G. Wait. The wait, as in like ABD.
Nah, C. What does C stand for? C.
Oh, I forget that. The reflection angle. No.
Nah. The
Yeah.
critical angle.
Oh,
Yeah. C is the critical angle. You understand?
yeah.
And I will share why is the critical angle as well. Share, give a reason. Jonathan, look at it, right? Check it out. So if this is the critical angle, notice something. Watch, you notice that? At the critical angle, the angle of refraction is?
42.
No,
No, it's 90 degrees.
90. Now I say that draw this diagram kind of dotish. That's my humble opinion on the matter. Because if Nemo looking at the fishing net, and he looking from water to air,
Yeah.
right, that's what really going on. So let me draw back that diagram in a way that will make sense for you guys. Emma, you understand what they're doing this question to tie up?
Yep.
Real madness, you know, boy. Real madness. They want to see all this suffer. Emma, will you suffer though?
Nope.
No, you're gonna suffer.
Hopefully good.
Yeah, John, I think you're unmuted. So that was, I just run back the diagram. Right? This is your normal. So Jonathan, so let me just say this is Nemo, right? Nemo kind of looking ugly now. I don't know what happened to Nemo, but Nemo experience are glued out. So this is Nemo over here. And the angle they give us, that was the what angle? This angle over here, that was what? That was
The
what?
critical angle.
Right. And now if you're at the critical angle, your angle of refraction is
90.
yes. So we have Nemo looking up over here. Right. Right, so Jonathan, this over here, that's really your angle of refraction, right?
Uh-huh.
I mean, if you understand what I brought so far.
Yeah.
Is anybody confused? Now is the time to let me know. Say now, are you going to get real loss?
No.
All right. So Desron, you understand that Desron, you want to call this way? You want to call she?
Reggie,
You ever run?
ascend, you know, we can check this back correctly.
Name the whale Rooney Lal.
Nah, that's not correct for him.
Okay, I just wanted to know. I realize something wrong.
I will explain.
Easy.
I
Huh?
will, I will explain why it was wrong, eh? I will explain why.
Alright.
So Varun, they put out 42 degrees and thing just to tie up, you know. Let me show you what actually going on. If Nemo in the water and he looking up at the fishing nets and they saying that this is the critical angle, then he will be seeing the fishing net like perpendicular to the water.
Yeah.
Because Jonathan, this is where the fishing net actually is, eh? That's where it actually is. But since Nemo looking from water to air, will he see the exact location or will it be bent?
It'll be bent.
Varun, that makes sense, right? Because light travels different in water and air. So he not actually seeing the fishing net where it's supposed to be. He's seeing it over here. You understand? Varuna.
Yeah.
You sure you understand that?
Yeah.
Okay, so I draw back the diagram over here, right? And name this Mira.
And Mira was the ostrich.
Well, use your ostrich now. Right? So Varun, Mira, she's swimming in the ocean and she looking up, she about to get caught. Use the fisherman. You're gonna catch she in your nets. Right? You just handle it skillfully, right? So Mira will be looking up from the water to the air. So this over here is really the angle of incidence, and this is really the angle of refraction. So, Varun, what did they say about this angle over here? They said that it was C. You see this little symbol on top here? Watch.
Yeah.
That means the critical angle. At the critical angle, what we know? What we know at the critical angle?
It's 48.
No, what we know that's happened at the critical angle.
The
Go up to the notes.
the refractive
What happened at the
in
critical?
the refractive index is bent directly to the normal. It's from a 90 degrees.
Right, the angle of refraction is 90 degrees, right?
Yeah.
So watch. That is the 90. Look at it. You see it?
Yeah.
Look at the diagram. Tell
It's
me.
how to put the diagram at real confusing.
I know, but look at it. The critical
Yeah.
angle here, and you see the 90 degrees. Bam. So we know that the angle over here, the angle of refraction is the 90 degrees. And we know that C is Jonathan M2 is 48 degrees. All right, Jonathan.
Alright, go on.
And C was 48. Yeah, C was 48.
Yeah, that's 48. I thought you correct this, Jonathan.
Nah. So read part 2 from Jonathan.
Given that angle C is the critical angle for the air-water boundary, calculate the refractive index of the water.
Okay. So Jonathan, Meta is looking at, is it going from water to air, water to air. So, gonna handle it carefully. First of all, tell me, where's the formula I'm going to use? Anytime I'm going from one medium to the other, what's the formula I'm going to use?
From medium?
Yeah,
Oh,
one medium.
speed of light over speed of the medium.
Nah, we're not trying to. You see, Jonathan, you wouldn't use
Huh?
a formula here because they gave you no information, none at all about velocity. You don't have a single bit of information. Anytime you're going from one medium to the next, you just use this formula for Snell's law. You're gonna use Ni sin I is equal to Ni.
Oh,
Because look at the information we have, Jonathan. We know what the refractive index of air is. We know what the angle of refraction is. We know what the angle of incidence is. We know everything. So that is why you had to use this formula. You understand?
yeah.
So Jonathan, I start off where? Where I start off in?
It starts off in
Where's Midha?
the water.
Water. Do I know what the refractive index of the water is?
No.
Nah, so I'll leave in that blank. Ni, you don't know what that is. If you want to, you could replace that with NW. That's Ronnie, understand what's going on? So Midha is in water, so that's where you're starting off. That's the angle of incidence,
Yeah.
right? Then we just change it to theta I, right? Yeah, so we could call it NW, that's a refractive index of the water. And Jonathan, do we know what the angle of incidence is?
Angle and yeah,
What it is?
90.
No,
No, oh wait, the 48.
48, yes. And now since our 48 degrees is your critical angle as well, where's your angle of refraction?
90.
90. And you're going from, and Desron, you're going from water to air. Where's the refractive index of air?
Is 90?
Here we're saying a refractive index in air. Does light bend in air?
No.
Nah, so the refractive index on air in air is 1.
Oh, 1. Okay.
I think he was talking about the angle of refraction,
Yeah.
right? So that, Jonathan, since 48 degrees is a critical angle, R will be what?
R will be 90.
Right, so Varun, that was the mistake you made. So Varun, look at that again. 48 degrees is a critical angle. If 48 degrees is your critical angle, then your angle of refraction have to be what?
90.
90, yes. Yes. You understand now?
Yeah.
Right, and Jonathan, where's sine 90?
So what?
Where's 1 by sine 90?
Sine 90. It'll just be
1
oh no,
by
your accent. Oh, it'll just be 1.
1. Okay. So, Desron, if I want to find the refractive index in water, which is NW, what I have to do on both sides? So I'm trying to find for this.
Divide by sine 48.
Yep. Mm-hmm. Right? So, Jonathan, tell me what your refractive index of the water is. Is 1 over sine 48.
One 1.3456.
Right, so round it off to 2 dB.
1.35.
Right. Mira, you understand that question completely?
Yeah.
You're sure, like absolutely clear.
Yeah.
Okay. Cheyenne, you good with this question? Can you hear from me now? Or like, you have anything that confused you?
No, okay.
Right. So the answer for part 2, that is 1.35. Varun, how you feeling? You okay with this?
Yeah, good.
Emma, I didn't hear from you in a while. You understand it?
Yep.
It's just drawing diagram kind of weird. Because, and you know that if you had the critical angle, if your critical angle is the angle of incidence, and the angle of refraction is 90 degrees, you know that, that's a fact.
Mm-hmm.
But if you're doing this question, the arrows might kind of throw you off, and
Huh?
Yeah.
because look at that. This over here, this could be your angle of, like, it's real confusing if you look at the diagram they give you. Real confusing. Mm-hmm. We understand it now, right?
Yep.
Okay. So Jonathan, let me finish off this question. So get this I read from my Jonathan.
Nemo swims away and his eyes is now a horizontal distance of 5 meters from point B. Looking at point B, he no longer sees a net, but now he sees Bruce, the shark.
Jonathan, I like how they have to specify, but now he sees Bruce, comma, the shark. Oh, that was hilarious.
I don't think Bruce went to the dentist. He missing something.
Yeah, boy, like it. Yeah, real make Bruce PG rated. Like PG 13.
Yeah.
Don't wait. Hey, made her I feel Bob Cock or Bruce, you know. I feel like what happened. Bruce on teeth. Yeah. And all they notice half of Bruce body missing too. Yeah, I don't wonder what Bob do to Bruce. That's crazy, guys. Wait. Yeah. So Jonathan, continue the question.
If Bruce is at the same depth as Nemo, how far away is Bruce's eyes from Nemo? And explain your result.
Okay, so Jonathan. So Nemo swims away. If he swims away, the angle of incidence will it get smaller or bigger if he moving away?
It'll get bigger.
So I want to remind you what has happened when you pass a critical angle. So Jonathan, if this was a critical angle over here and he swim away, what's going on right now?
The critical angle getting larger.
So what's going on right now? If you go beyond the critical angle, what has happened?
The effective angle will get smaller.
No, I haven't seen it.
Total and general effect.
Yes, that's what has happened. Let me just show back the example of it. So, Jonathan, if you increase the angle of incidence past the critical angle, eventually it will bend so much, it will bend into its own medium. So look at it over here,
Oh,
and that is total internal reflection. If you pass a critical angle, it is bending on itself, and now you're going from water to water. So you have total internal reflection. So that's what happened over here. And you can see it yourself. Check it out. See it?
yeah.
So if you have total internal reflection, see if you can figure out the rest of the question. See if you can figure out how far is Bruce's eye from Nemo's eye.
Would it be like the same distance?
So you're saying that this could be 5?
Yeah.
So then how far Nemo will be from Bruce's eye?
10?
Yep, 10 is the answer. Mira, you understand what's going on there?
Yeah.
So when Nemo swam away, what happened is he went further than the critical angle, so now he's seeing Bruce. Yeah. Emma, you understand this application type question?
Mm-hmm.
So Jonathan, I noticed you had trouble connecting the concepts. A little bit. A bit of trouble. Yeah. Is it like because of practice or something, or?
Huh?
I noticed you had trouble connecting the concepts, but in AdMaths, you don't have a single problem with connecting the concepts. It's just in physics.
Physics.
It's just
Those
physics.
work my brain does work differently for some reason.
So let me just give a little reason in here. So made her explain this question to me. Why Nemo seeing Bruce when Bruce behind him? Wait, Jonathan, that's so weird. Think about it now. That's actually happened. Like fishes will see things behind them. You think that's
Oh
weird?
yeah,
That's so weird. Huh. I never thought about that.
because they refract, yeah, refracted. Well, it just go back on itself.
That's so weird.
Uh,
Emma, did you ever thought about that before? Or like that's so cool now. It's like fishes will see behind them. That's crazy.
Mm-hmm.
Why I think when something come in, they just swim away without turning around.
That is why now I know. I never thought about it before. But now I understand why. Yeah. That's really cool. Right? So Meta, just explain the question to me in terms of physics and thing. So you have to get your 3 marks, you have to include the critical angle, right? You had to include the critical angle, you had to include total internal reflection, and you had to include, if it's a and you had to talk about total internal reflection, the properties of a reflection. Properties of reflection. Yeah, so you might
The When the critical angle surpasses the boundary, it turn it turns into
nah,
an angle of refraction.
the critical angle, not passing the boundary line, that'll be over here.
The angular incidence.
When the angle of incidence surpasses the critical angle. And
Total internal reflection happens.
right, but here what you gotta apply it to the question. So you gotta say, because Nemo swam away, the angle of incidence would now become greater than the angle of the critical angle. You gotta say them again. Total internal reflection happening. So this the properties of our reflection.
The angles are equal.
Right? The angles are distance. The angles are equal. And what about the object distance and the image distance?
The image distance and the object distance are equal.
Yep. So that's perfect. So just say Nemo will be 10 meters away from Bruce. Right? So I'm just follow reasoning here. But this was the hardest question, I think. Emma, what do you think about this question?
It was interesting.
You don't really see them apply it to scenarios like this.
Yeah.
Right? So by Nemo swimming further away the angle of incidence would now surpass the critical angle. Once the critical angle is surpassed, total internal reflection is right. And Cheyenne, tell me the properties of total internal reflection. If it had total internal reflection, what's the properties? kind of hearing Cheyenne. So,
Wait.
okay. So,
The angle of incidence must be greater than the critical angle. And the light moves from a more dense medium to a less.
nah, that's not what I'm talking about. I'm talking about what has happened at total internal reflection. So, at the total internal reflection, the angle of incidence is equal to what?
The angle of refraction.
So at
Okay.
total internal reflection, the angle of incidence is actually, you don't say angle of refraction, you know. I was checking it some textbook. It is actually say the angle of reflection.
Okay.
So you have to talk about that. So at total internal reflection, the angle of incidence is equal to angle of reflection. Therefore, the object distance, because it's a mirrored image, it's like a reflection. So therefore, the object distance will be equal to the image distance. So then you say, therefore, Nemo is 10 meters away from Bruce. Right, Jonathan, you understand that perfectly?
Yeah.
Yes. Deshaun, how are we feeling? Like you understand this question? Well, I'm wondering if anything confused here.
Yeah, understand, to be honest.
Okay, nice. So you understand that because he swim away, the angular,
I could have find the 5.
the 5?
Huh?
You say you could have find the 5?
Yeah, I have 25 centimeter now.
You could have, I mean, you could have find it.
Huh?
Like if you could have calculated,
Mm-hmm.
that would be kind of,
Well, I could have find it, I mean now.
or by looking at, because it was a total internal reflection.
Yeah.
So you understand that because he swam some further away, he passed the critical angle, and anytime he passed the critical angle,
Mm.
it is now go down in. It's go down into the medium and it's be reflected.
Yeah.
Chief, I have to go
When
now.
it's to explain it though.
Wait.
Nah.
Made her, no problem. That's it for today. Made her, you feeling any better or anything? This is the end.
Yeah, I understand it more. I just think as we do it now, I'll just print it over, the blank one, and I'll try it myself.
Okay, no problem. Right? So guys, that is it for class today. We finished waves and optics. So yeah, guys. Have a good night. It's
Yeah.
Later.
later.